Okay, so welcome. Welcome everyone to the 15th edition of the Lisbon Machine Learning Summer School. So I'm Bruno, one of the co-organizers. Before we move on to the first lecture here today, I have some announcements regarding the organization of the school and the logistics for the next couple of days, okay? But this will be fairly brief. So, well, since the first edition, the school has been hosted by Instituto Superior Técnico, so also Técnico, okay, it's an alternative, shorter name. So Técnico is the engineering school from the University of Lisbon. And throughout the years, Técnico has been very supportful of the school with the facilities, with helping dissemination. We are very grateful to Técnico. So some of you perhaps maybe consider visiting us later on a future opportunity, perhaps joining one of our programs, perhaps through a short Erasmus visit. So in case you are interested, Técnico indeed hosts a series of different programs related to machine learning, NLP, and related areas. And on the website over there, you can find some additional information on this. Okay, so Técnico is also home to the ELIS unit Lisbon, so one of the units of this European Laboratory for Learning and Intelligent Systems. Several of the researchers involved in the school are members of ELIS, and again, on the websites you can find some additional information about programs and activities related to ELIS. So we are also very grateful to our sponsors and supporters. Okay, so in particular, Google and Zendesk have provided us with the funding through which you are giving some of you scholarships that support your registration and expenses here. Several other supporters are giving us in-kind contributions that are very, very helpful for the school, and we are indeed very, very thankful to them. So there's a large list of people that are involved in the organization of the school. So you have their photos here, even though, well, perhaps some of these photos are from their former selves. Throughout the week, these people are going to be here. You're going to have opportunities to talk to them and to interact also with the organizers. Besides the organizers, so the school also has a steering committee. Some of these people have helped a lot in the beginning in the organization. Some of them regularly still meet to discuss the school and how the school should evolve. So very importantly, in connection to this, on the last day, we'll be giving you a form through which you can give your suggestions and feedback regarding the school. Okay? And we indeed take that into account, and we try to plan future editions taking your feedback into consideration. Okay? So please do fill out the form. Also very important are the monitors. Okay, so throughout the campus you'll see people wearing either dark blue shirts with the logo of the school or orange shirts. These people can help you find your way around the campus and, well, with any other particular need that you may have. Some of these people were involved in preparing the labs or more in organizing the activities. Others are going to be in the rooms in the afternoons where we will have the lab sessions. Okay. I would suggest giving a round of applause to the monitors because they are truly, truly important. Now, okay, logistics. So we are right now on this building over here, the IST Congress Center, which is also the civil engineering building. So the morning lectures, the evening lectures, the morning coffee breaks, all of them will take place here in this building. Okay? You'll also have lunch in this building on the ground level floor. And again, the monitors after the first session will help you find your way to the place. Okay. In the afternoon, you'll be having lab sessions on a different place in a building from the informatics department, which is located more or less, so more or less here. So if you go out this building, so this is the central building of campus, you can move either through here and then from the back all the way here, or you can go through this place here. So again, the monitors will help you find the place where the labs, well, will take place. And every afternoon, the evening lecture takes place here as well. There's an afternoon coffee break on almost all the days of the school, except today, where in the evening we'll have a welcome reception. Now, this welcome reception will take place either on a different garden next to the chemistry building or right here in front of this building. Okay, so the problem is that that other place usually is too hot. So again, we'll have the welcome reception in this case exactly in the same place where in the other days the afternoon coffee breaks will take place as well, which is the afternoon, sorry, the garden outside of this building by the afternoon. Okay. So again, there's a Discord channel associated with the school. We'll be placing announcements, updates on the schedule, any additional information. You can join this Discord channel for these regular updates. On the website, we'll be reflecting this as well. The lectures will be broadcast to YouTube as well, and after the school, we'll be posting there the recorded versions of the lectures as well. Okay. Regarding the schedule, you have the complete information on the website. Every day the program is kind of similar, so with the morning lectures and evening lectures. Okay, so the schedule for today is this one. After these brief notes, we'll have a lecture focused on learning with linear models. Then by 10:30 we'll have a coffee break. We'll have lunch at around 12:30 here in this building as well. And then in the afternoon you'll have the lab sessions on this other place. Exceptionally today, by 5 p.m., we'll have a welcome reception on the garden in front of this building. Okay. The other days, or for the other days, you have the schedule on the website. So I imagine that for most of you, you'll be having Wi-Fi access through EduRoam. It's pretty simple. If that's not an option for you, there's this other network that you can join, Technical Guest, using the username and password that is listed here. There are some sheets outside with this information as well. Again, updated information will be posted on the website whenever necessary, and there are also these Discord groups or Google groups where additional dissemination will take place. Okay? So on Tuesday next week, we'll also have a social event, a banquet. It's traditionally in this school always in the same place. There's this restaurant downtown called Casa do Alentejo. Perhaps we'll be going there walking as a group from here. Some of you may join as well from the metro substation. Okay, so there's a metro substation station nearby. So the address is posted on the website. You have a link with the coordinates for the place on the website as well. And well, this QR code here, I guess it directs you to the web page of this restaurant. Okay. And well, regarding these introduction notes, I guess this is it. So enjoy the summer school. And let's welcome Mário Figueiredo, so a distinguished professor here that has been giving a similar lecture, I guess, since the very first edition of the school. It changed? Well, it used to be Introduction to Probability and Statistics, and now it's more learning-oriented, okay? So let's give a round of applause to Mário.
Thank you, Bruno. So, good morning, welcome. Yes, I've been teaching on this school for 15 years now. Actually, 14 years, it's the 15th time. This is a picture from sort of midway, it's maybe like from 7 or 8 years ago. Okay, but it changed quite a lot. So in the first editions, I was mostly, I need to change this. I'm sorry. I'm going to change this too. Okay. Okay. So in the first actually first couple of editions, I gave a few lectures on how to infer graphs from network data. It was nothing to do with what we're doing today. Then for several years, I taught half of the morning session of the first day. One half was about introduction to Python, which kind of is not doesn't make much sense these days, by Luís Pedro Coelho. And then I would teach the second half on the refresher on probability theory and algebra and stuff that's needed for machine learning. And then in the last few years, like 3 years, so actually this was inherited from André, who taught this version or the idea of starting with linear models like 4 years ago, and then I took over like 2 years ago. So it's about learning with linear models, and it's basically about some foundations of machine learning for some aspects that I think are very crucial for understanding machine learning, and I will justify why we think this is very important to start with. It's also so this is probably a very heterogeneous audience. Some of you will know a lot of these. Some of you, for some of you, this is probably first time, or not the first time, but you haven't seen it from this perspective. For those of you who have seen this before, you can enjoy the ride and maybe think that I'm not explaining it too well. For others, I hope you learn something new or say at least some new perspective. So machine learning is typically divided. This is a very simplistic view in these two main branches, supervised and supervised. And in supervised learning, it's mostly classification and regression, depending on whether we're estimating or predicting a quantity or a class. And we're going to be staying on the left side. So I really like this painting, which should be appearing soon. Nah, it's frozen. It's not sharing anymore. No, it's coming back. I hope. Otherwise, we'll just change the setup. Okay. Yeah, problems with our network. It is sharing. I can see it there. I don't know why it's not showing there. We tried it before. It worked. Yeah.
Se calhar tirar dali o ecrã.
Não, já está, já está. Não, já está.
Exato.
Já está, já está. Mas não está, ele não está a partilhar para ali. Okay, let's try to just share from here.
Eu digo qual é a sessão.
Tinha que procurar onde é que está o zoom.
É carregar aqui em cima.
Onde é que está o zoom?
Escrever zoom.
Pois.
Exato.
Deve
Está
ser.
bem. Tirar o vídeo de manhã. Pois, tirar este vídeo aqui.
Como é que se tira isto?
E tirar o som.
Ah,
Aqui deste lado. Aqui deste lado. Isso. É o contrário. Exato. Pronto.
preciso disto.
E agora,
Como é que eu faço o vídeo?
tem aqui uma opção.
Ah, pois, está tão lento.
Portanto, exato, menos.
Ok.
Agora, já está.
Que porcaria. Ah, é para ver aquilo, não é?
Continua com o som. Bem, não será grave, se calhar. É de facto estranho estar ali o. Exato, é esse mesmo.
Ah, ok.
Fantástico. Pronto. Tá?
Okay. Why did you give me sound here? Okay. Okay, can you hear me?
Mas está aqui a aparecer som.
Foi, mas está no mínimo.
Só um bocadinho aqui uma coisa. E onde está aqui? Logo. Sim. Vai aqui, tirar aqui.
Ok? Não, está a continuar a dar.
É?
Não faz mal.
Agora já acabou.
Oh. Oh. Okay. Okay, sorry for these. So as I had, yeah. So this is not such a nice setup because it shows the tools up there. The other setup is much better. So as I was saying, I like this painting, which kind of illustrates the idea of supervised learning. It's someone supervising the learning of a child. So that's the idea that supervised learning is about getting supervision on what you learn. And there's this picture kind of illustrates the many different types of machine learning. It's kind of a bit outdated picture in the sense that it doesn't contain something that we'll talk very briefly about, which is self-supervised learning. It contains only unsupervised, supervised, and reinforcement. But the sound is still here. It's very annoying. Yeah. I don't know why. Sorry. Wait, there's no way to mute. Even the Zoom is without connection.
There, share device audio. Okay. Optimize for video. Okay.
It's probably okay.
Yeah.
No?
No?
Yeah. Can you hear there? Yeah. Can you hear the echo? No, it's okay.
It's
Okay.
okay,
I
it's
can
okay.
I can put up with it. Okay, so yeah, sorry. Classification. So on that corner there, unsupervised learning, which has many different applications, from predicting stuff to classifying images. You've all seen these before. We will not talk about anything other than classification and regression, which I'll very briefly define more formally. And of course, you may ask, why study linear models, given that we are in 2025 and everything is about deep learning and deep neural networks? Well, there are lots of good reasons. So one of them is sort of the underlying machine learning concepts are the same. Okay, if you want to understand deep learning, you need to start by understanding linear learning, because mostly the trade-offs and the language and most everything is the same, and it's much easier to understand in the linear case, both mathematically and intuitively. The theory is much easier to understand, so there's very strong theory for linear models. We won't go a lot into theory, almost anything at all, but especially in the optimization side, it's much easier to understand, and much easier. And if you don't understand things in the simple case, in the linear case, then there's no hope of understanding things in the much more complicated deep learning situations. It's still widely used in practice. Okay, especially if data is scarce. There's a lot of linear models being used every day around the world, many. So it's still very used. It's not that deep learning made linear models obsolete, not by any chance. They are a component of deep networks. So in a sense, every neuron, I don't like the word neuron, but every neuron in a neural network is sort of a little linear model. And the final layer of most most deep networks is a linear model. So it's very important to understand the components of deep learning. And it's sort of a natural point for studying machine learning. In a sense, it's sort of the spherical cow. I don't know if you've seen this analogy before. So the spherical cow is an analogy that's much used to make fun of physicists, where you think of a spherical cow, because of course there are no spherical cows. It's in the sense, it's the idea that you abstract all the complexities and focus on a very, very simple model that you can understand simple stuff like force equals mass times acceleration. And so this is kind of so linear models are sort of the spherical cow of machine learning, where everything is much simpler and everything is supposedly easy to understand, and it's a fundamental starting point. I also came recently across this advice by this guy called Eduardo Ordaz, who's an AI lead. He's a generative AI lead at Amazon Web Services, and he has these. So he's not working on linear models or in mathematics, but he has this advice, which is math is all you need, or at least the best place to start. So the fact that you can have that linear models are an area where you can be closer to the mathematical foundations is a very important aspect. And so of course he goes on to say, don't get an AI degree. The curriculum will be outdated before you graduate. Instead, build a strong foundation in math, statistics, and physics, and stay up to date with AI through code focus books, blah, blah, blah. So if in short, if you're solid in math and willing to refine your coding skills, you'll be a valuable asset to any top AI lab. And actually, I can confirm this because I know someone who just finished his PhD a few months ago, and he's applying for some top labs. And the other day I met him, and he was carrying just a probability and statistics book. He said, "Why are you studying probability and statistics?" "Oh, because I've been interviewing for some companies, and they're asking me basic probability questions. If you have 2 decks of cards and you shuffle, what is the probability that you get, blah, blah, blah." And I don't remember this stuff, so I need to refresh my memory about this basic stuff. So it's important to know these basic things. Okay, so this picture is supposed to illustrate the idea that by looking at linear models, you're also looking at deep networks, because essentially the final layers of deep models, say classifiers, are just a linear classifier, where everything that's behind is just feature extraction, okay, which we will learn a lot about during the school. But today we'll focus only on the red box, on the final layer, assuming that feature extraction is something that has been taken care of, and that we know how to, and that we just worry about how to learn, how to design the final layer. And we're going to be in a position where we're not going to do standard stuff like gradient backpropagation or anything like this, but we're going to try to do it as formally as possible, because this is the only case where you can hope to do it, to analyze exactly what is going on. So the outline of the lecture will be something like this. I will start with a more formal introduction in a second. Then there'll be essentially two sections. It's a bit faint, but you can see it. About one section about regression, which is when the task is predicting a quantity, and the other section about classification, which is when the task is predict a class. And I'll talk a little bit about what we mean by a class. It's not totally trivial. And finally, there'll be a section which is very important for machine learning these days, which is optimization. Okay, optimization for machine learning in general, specifically for supervised learning, and which will be the foundation for other lectures, that because optimization is everywhere in machine learning. Okay, so notation. We always deal with some input. So the machine that we're going to build, machine learning is about learning a machine. We'll have an input which we typically call X. It belongs to some set big X. It can be many, many things. Okay, it can be a news article, an email message, a face image, a collection of lab test results, some features of a credit card transaction if you're doing fraud detection, features of a car, features of a house, if you want to say predict the price or whatever. The output can be, again, one of many different things. It can be a decision whether this news article is fake or true if you're doing assessment or detection of fake news, or spam or legitimate email if you're doing spam detection, identity of the face, blah, 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 etc., etc. So you can think of infinitely many examples. So an input-output pair, of course, is a pair of these things. Is, for example, it could be a news article together with the topic if you're doing, say, topic classification for news articles, or a sentence together with its translation in machine translation, a sequence of words or tokens together with the next word. That would be an input-output pair if you're training a language model. An image partitioned by a human if you're learning how to segment images. So you can think of, again, infinitely many examples. And the goal, of course, is to build one of these little boxes that knows how to predict what you're interested in. So, for example, it takes email messages and classifies them as being spam and sends them to the spam folder, or classifies them as being legitimate and sends them to your inbox. Or it can be some model used in a hospital that, based on features, some observations, some lab tests, and some properties, age, blood pressure, whatever, of a patient, estimates the length of stay in the hospital because that's important for the management of the hospital. Or it can be a language model where that takes the previous word in a sentence and tries to predict what the next word is. Okay. All of these are just decisions. It could be called classification, prediction, regression. They're all decisions. You decide what comes next, what the estimated length is, if the email is spam or not. And before we go on to learning, let's look at what we mean by optimal decision, because we're trying to find good decisions. Of course, we all want good decisions. What we mean by good decisions, or hopefully optimal decisions. Okay, so the ideal situation would be a situation, and the ideal situation for me is assuming that you all know a lot about probability and statistics. And if I say I have a joint distribution of two random variables, you kind of know what I'm talking about. Okay, so I have two random variables, X and Y, the input and the output. And the ideal situation is if some God gave you the joint distribution of the world. So these two features have this distribution, okay? And you're very glad to know about that. And from that, you may ask, how do I make good decisions, knowing how the variables depend on each other, how they are related? And you need something else, which is how to assess the quality of a decision, okay? And the quality of a decision is assessed by something which we call a loss function, which is just a function of two arguments, two decisions. And it kind of measures the loss that you incur by deciding, say, y hat, when the true label was in fact y. So, for example, what is the loss that you incur if you classify an email as spam when in fact it was not? Okay, or if you choose the wrong words when you're training a language model, if you predict the wrong word, what is the loss that you incur? So we need these. This is a fundamental object in machine learning and decision. And if you know the joint distribution, if you know how Y and X are distributed, then you're in a position to find the optimal decision, in the sense that you can compute the expected value with how much you expect to lose, what's the expected value of your loss, because you can compute this expected value because you know the joint distribution. Okay, and then you just integrate across all possible inputs, all possible outputs, the loss, the prediction, the loss computed with the actual value and the prediction, integrate, multiply by the probability density function, integrate, or if it's discrete, you sum instead of integrating, and you find what is the function that minimizes this expected value. And this is called an optimal decision. This is the topic of a big area in statistics called decision theory, which is how to choose optimal decisions in the ideal situation where you know the joint distribution. Okay, this is not the case in machine learning, of course, otherwise we wouldn't need learn. But it's important to know. As we know, of course, unfortunately, the joint distribution is seldom known. Sometimes we assume something about it, but it's seldom known. And so we need to replace these unattainable computation by something that we can do, which is called typically supervised learning. Okay, and in supervised learning, in essence, the difference from optimal decision is that you don't know the joint distribution, but you have a collection of pairs, of input-output pairs, which are called training data. So you have a lot of examples of input and correct or desired output, say n of them, which is called the training data. And what makes sense is to learn a predictor. You want to learn a predictor, so something that takes an input and produces an output. And there are typically two standard approaches when you don't know the joint distribution, so you cannot compute the expected value of the loss. One, it's called generative approach, which is, okay, you have data. And so although you don't have the joint distribution, you can estimate the joint distribution from the data. You can factor it if you want. You can factor it using Bayes' law, which I'm assuming all of you know, P of A given B times P of B equals blah, blah. You can factor it, or you can just estimate it somehow. You can estimate the joint distribution from the data, and then you go back to the previous slide, and you compute the expected value using this plug-in distribution. Okay, this is called a generative approach to learning. It's very used too. It's very used. It's very old. It's kind of sort of mostly part of statistics, but also of machine learning. And there's the other approach, which is called discriminative, which simply proceeds by replacing the expected risk, which you cannot compute because you don't have the joint distribution, by its sample version. So you have samples from supposedly the joint distribution. You cannot compute an expected value because you don't have the distribution, but you can compute an average, which is called the empirical risk. The other one is the expected risk, which would be the ideal thing that you would like to compute, but you cannot. This is the empirical risk. And so you choose your decision function, H star will be the optimal one, by minimizing the expected risk. So this is why this is called empirical risk minimization, which is the average of the loss across all the training set. And the goal, of course, is to find what is the best function that I need to put here. Okay, that will minimize this empirical risk. Okay, so this is supervised learning in 2 slides. This is essentially this. Okay, of course, in this lecture, I will only focus on this bottom version, discriminative supervised learning. I will not talk about generative approaches and estimating probability density functions or anything like that. Okay. Okay. Let's go on. Okay. What about self-supervised learning? That's all the rage these days. You all know that all modern large pre-trained models and language models and all of that are learned using self-supervised learning. Where does self-supervised learning fit into this picture? Okay. Well, in its most basic form, self-supervised learning is just supervised learning, with the difference that the predicted responses are programmatically defined. You don't have to have a human saying this is a dog or a cat, or is this a valid or invalid email to train a spam detector. You create a data structure, a data set where the predictions are created programmatically. For example, when you're learning a language model, learning a language model is essentially learning a supervised learning problem where the correct label is the next word. And you don't need a human to tell you what the next word is because it's already there. You just uncover it and check, is it wrong or is it right? Okay. So self-supervised learning is just a bunch of many different techniques to create data for supervised learning, or there are other variants for contrastive learning. There are many different variants, but in the most simple version, the simplest version, it's just supervised learning with programmatically defined training outputs. So, but taking humans, so the fundamental thing is taking humans out of the loop. You have a way of creating data that can be used for learning without involving humans. So the classical example, as I was saying, is next word prediction. Please stop me, interrupt me if you think I'm saying, if you have any question, comment, if you think I'm saying. Sorry? There's a question where? Oh, down here. I thought you were pointing at the screen. In semi-supervised, so semi-supervised, you have parts. So you have a data set like these. collection of pairs plus a collection of only inputs without labels, okay? And so you're doing something which is typically, if you have only inputs, you want to do something like, which is typically called unsupervised learning. You want to do something like find out if this data is clustered somehow, or if they belong to some lower dimensional subspace or manifold. In semi-supervised learning, you have some of the data is labeled, some is not, and you want to take advantage of the fact that you have both axes and y's for some of the axes to help you in your learning task. And so in semi-supervised learning, you almost always need to use something which is a hybrid between generative and discriminative learning. Because for those data points for which you don't have labels, you cannot compute losses, these kinds of losses, because you don't have the desired label. So semi-supervised is a very different scenario, because it's for a situation where the data is, you're not producing data programmatically. For some reason you have data. Suppose you have many faces. For some you know the labels, for some you don't. But you can use the ones about which you don't know the data, you don't know the label, to somehow help you solve the problem. Okay. Okay, so supervised learning is divided in many different types of subclasses of cases, which are typically called classification, regression, and many variants. So in regression is when you're predicting a quantity, say a number. And classification is when you're predicting a category. And the category is a kind of a fuzzy word. What you mean by category is any set. The fundamental thing is that the set on which you're producing your predictions has no order. You can permute it in any way. It doesn't have the order has no meaning, like classes. Red, blue, green, it's just colors. You can put a set, so it's a set. It's actually a set with no order. When it's in regression, you have a quantity, so you're not free to permute the order. You're estimating a length of stay, so you need to produce a number, and numbers have a natural order. So you're producing a quantity, and it makes a huge difference in practice. So people typically talk about regression when you're predicting just one quantity, which could be a real number or a number between 0 and 1 if it's a probability, or a positive number, or whatever, something, or an integer or something, but it needs to be a number. Okay. In multivariate or multiple regression, you're predicting a collection of numbers, say a vector. Okay. For example, if you're denoising an image, if you have a noisy image and you want to produce a denoised image or an unblurred image, that's a multiple regression problem, because you're taking as input an image, you're producing as an output a collection of numbers, which is the value of the pixel at each, the value of the image at each pixel. Of course, there's classification, which could be binary, when the thing that you're predicting is yes, no, A, B, false, true, fake, not fake, spam, not spam. So in classification, a very important aspect of classification, and it's important to keep in mind, is that the labels have no meaning. Okay, they're just labels for things. There's no semantics. You can say A0, 1 or AB or red and blue or whatever. It doesn't matter. Okay, it's just a collection of objects. And in multi-class, you have more than two. Okay, and again, I stress the order is irrelevant. This is one of the fundamental aspects in classification. And there's another final case that I want to mention, which is structured classification, which is the case when the output, when your prediction does not have a fixed dimension a priori. Okay. For example, if you're doing machine translation, of course, you can see it as a classification problem, because the possible sentences that you produce as a translation of your original sentence belongs to a discrete set. It's all possible sequences of words in certain language. It's finite. It's not infinite, because it's infinite if you don't limit the length. So it's very large. It's exponentially large. If you're translating a big sentence, of course, the space of possible translations grows. It's bigger. It's exponentially bigger. And it's structured in the sense that there is some structure. It's not just a label. It's a collection of decisions that are somehow have some inner structure, like a sentence, okay, like language. Okay. Image segmentation is another example, because, of course, the number of decisions that you need to make when you're segmenting an image, which is to which segment does this pixel belong, grows with the size of the image. So you don't know a priori what the space of the decisions is. It depends on the input. Okay, feature representations. So typically, as you may guess, what we feed to these models is not an object. You cannot feed a sentence. What does it mean to feed a sentence to a classifier, which takes in a vector of things? We need to somehow find a way of representing the objects that you need to classify. And so feature engineering is, or maybe it was, an important step for linear models. So classical examples, maybe most of you have heard about these: bag of words for text or parts of speech, or if some of you worked on NLP and had the course on basic NLP, you've seen this before. In image, there's thousands of papers up to mostly the mid-2010, so 12, 13, thousands of papers on how to extract features from an image that allows to solve some classification problem, for example, detecting objects or something. There's thousands. That's what most people in computer vision did, was design features for solving certain problems. Then deep learning came around. There's many types of features, and there's decades of research in machine learning, in NLP, in computer vision, in image analysis, in speech processing, on designing clever features. Humans were very involved in designing clever features that were useful to solve whatever task they wanted to solve. Okay, so feature representation formally of some object is just a mapping that takes the object, whatever the object is, and produces a vector of numbers, which are the so-called features. So we will use always the representation of some object as a vector of features. Sometimes I will omit the phi of x. I'll just assume that the x itself is the set of features, is the vector of features, not a set, is a vector. And this is typically called a feature map. Okay, maybe it's a high-dimensional feature vector, maybe it's high-dimensional. It can mix categorical and continuous features. You can have some of the components of X are numbers. So if you have an electronic health record of a patient, which is a patient seen as an object, the features of a patient, some of them are numerical: age, weight, height, blood pressure. Others are categorical: gender, if it smokes or doesn't smoke, or something like that. So you can mix both categorical and continuous features. Often, categorical features are represented using a binary vector, which has the dimension of the number of possible values that feature can take, with a 1 at the position of that category. Or in other approaches, more modern approaches, categorical features, for example, words in a sentence are in a sense categorical features, because there's a finite number of words, and if you have a sentence, the word that appears in the sentence is a feature of that sentence. It can be represented by a vector, which does not necessarily have to be one of those one-hot encodings, which is called an embedding. So this is representing objects using vectors. It's called embedding. There's embeddings for many different things, but mostly visible these days is embeddings for words or tokens in language models. Okay, so in a sense, the conclusion is that feature engineering is sort of alchemy. You need to know a lot about the field. It requires deep domain knowledge. It's usually very time-consuming, but it's important sometimes. It allows incorporating knowledge. If you know a lot about the domain and you want to you know that some of your knowledge about that domain is important to design a good machine learning system, then it's good to impose that. We'll see about that in later. And it's a form of inductive bias. You can sort of guide the learning procedure into somehow satisfying some sort of properties that you know that the data has, or that the problem has. And you can do this by somehow engineering your features. It's still widely used in practice, of course, mostly when you don't have that many data. So learning features, as is done modernly in deep learning, requires, as you all know, a lot of data. But the modern alternative, of course, is learning representations or learning features, which is sort of synonymous to deep learning. As some of you will know, probably the biggest conference on deep learning, which is ICLR, International Conference on Learning Representations. It's not called International Conference on Deep Learning or International Conference on Deep Neural Networks. It's called International Conference on Learning Representations. And it's essentially a deep learning conference. So deep learning is essentially synonymous to learning features and learning representations. That's why ICLR, how it's known, is called what it's called. Okay? And this will be the topic of Monday's lecture. So there will be a hard fork now with fork into deep learning, but that's not what we're going to do today. Okay, let's look more closely at regression, and as we go along, we'll get a bit more technical. So if I want to show a picture to someone who knows nothing about what regression is, I'd show some picture like this, right? Everybody's seen regression sometime in their lives, even people who are not technical, even lawyers, even people who have no education, kind of. If you've seen a newspaper, just general public newspaper will have sometime a picture like this, where this is something, okay? And it's trying to predict how much chocolate consumption increases the possibility of winning Nobel Prizes, which is a nice example for causality. And so linear regression is just fitting a straight line. The first idea is just fitting a straight line to a bunch of points. Yes. And I like this. This is a bit outdated now, but I used to like this sentence a lot, which is Baron Schwartz said this in a lecture some years ago. When you're fundraising, you say AI. My company does AI. When you're hiring, you're looking for people who know about machine learning, which is actually what AI is all about. But you're implementing it in the end. If it's just linear regression, sometimes you can get away with just doing linear regression in many situations. Okay, but nowadays. I can't resist saying this. So Ben Recht, which is a professor at Berkeley, very well-known professor in machine learning and control theory, the other day tweeted or posted somewhere about something I said. Calling least squares regression AI is a bit of a stretch. But it's what everybody nowadays do. If you're doing, even my president of my department, my friend Jose Alberto, the other day said, if you're doing multiplication tables, if you're using multiplication, if it's above the multiplication table above 7, it's already AI. So everything is AI these days, but it's a bit of a stretch. Of course, when we talk about linear regression, we can actually be doing, and we will see that, non-linear regression, okay? So we will see exactly what the linear word means, and maybe some of you, well, most of you will know what we mean by this. So linear regression may in fact be non-linear, okay? It depends on how you set up the problem. And the way you choose your non-linearity, let's say, is a very important aspect of it. It has this inductive bias, and that's, I don't know if you can see, but I can zoom in. Okay, so this is an XKCD cartoon. If you don't know XKCD, I highly recommend that you follow XKCD, which is when if you have a bunch of points, you do linear regression, and you can brag about it. Hey, I did linear regression. But if you fit a quadratic function, you also can do a fit, and then it seems to show that there's a positive trend. But if you fit a logarithmic function, you can also do a nice fit, and it seems like there's no accelerating trend. It seems like it's tapering off. And if you fit an exponential function, you say, whoa, it looks like it's growing uncontrollably. Okay, and if you fit some other function, if you fit just an horizontal function, just fit the mean, you say, I'm making a scatter plot, but I don't want to, and you can go on, and different choices will carry different messages. So the title of the cartoon is "Curve Fitting Methods and the Messages They Send." So the way the things you choose when you're solving a machine learning problem or a statistics problem is very important. There's this inductive bias that you carry into the problem with your choices, and it's very important to be aware of them. Okay, so more technically, what exactly is regression? So in a nutshell, is the goal or the task of building a machine that predicts or estimates or guesses some quantity. So the key word here is quantity, otherwise it's not called regression, from some other quantities or features. I'm not going to be very specific about what they mean. So there's an input, an object, which is characterized by a collection of features, and you want to predict some quantity. And of course, as I mentioned before, this is a fundamental tool in data analysis, in much of science. All of the sciences use regression sometime, and in engineering too. So it's a fundamental topic whenever you're analyzing data of any form. And of course, the goal is to, given a collection of examples, so you're going to learn this machine, find out what's inside this question mark, from a collection of examples, which is called the training data. So the goal is to find the best. What we mean by best, we need to find out predictor or decision function from some set of functions. So this, I will use sometimes this capital H to mean the set of functions which are allowed in your problem. So you're forcing this box to contain a function from this class of function, not any function, one of these functions from this class. Okay. And in the following slides, I'll be a bit more careful with the notation. I would typically use bold notation like that to denote vectors or matrices. Sometimes I forget, but most of the times. Okay, so when we say linear regression, the first in the most basic idea is that this set of functions H only contains linear functions. Actually, it's not linear; it's affine. Affine means linear plus a constant. Okay, it's a straight line, but doesn't need to go through the origin. And so it does this bias, this offset W0 plus some linear combination of the features that you're forcing your function to have this form. That's what's called linear. Although it's not technically, it's not linear, it's affine. We always just say linear. And this thing here is just the inner product, just as you recognize it as an inner product between a vector W and a vector X. And so just to know where you come from, and people from different backgrounds use different notations for inner products. So in linear algebra, typically you write that as a linear product. It's W transpose times X. If you come from mathematics, maybe you write inner products like that, angle brackets, or in physics, maybe physics that also means averages. You write inner products like that. Typically in machine learning literature, people also write inner products with a little dot. So there's lots of notations, but it's still an inner product, which is just this. Okay, it's just the sum across all the components of the two vectors of the product of the corresponding component of the two vectors. So this is what linear regression is. It's just, okay, let's force the function to have this form. And then typically there are many losses you can use. So we need to assess how good a prediction is. And the standard loss is the quadratic loss, which is, okay, let's penalize the square of the error. So I'm predicting y hat, the true value is y, or the given value is y. I will penalize this as a square of the difference. And you may ask, why the square? Why not the absolute value? Yeah, that's also valid. Why not the fourth power? Why not the cubic function? Cubic doesn't make sense, right? Because you want to treat negative and positive errors equally? Not necessarily. Maybe you think that overestimating is more serious than underestimating. So you may want to have some function that grows differently in both directions. So you can think of whatever you want. It depends on the problem. But if no good reason to choose anything else, this one makes sense. And it has the real reason why it's used is because it's easy to deal with and it will lead to an easy problem. That's the real reason. People may argue about other things, but the real reason is because it's tractable. Okay, so you come up with excuses to use it, but the actual reason it's because it's easy to deal with. So if you have this loss, then all you have to do, remember we've seen this empirical risk, which is the average across all the training points of the loss function between the prediction and the actual value. You just take the prediction has this form that we saw up there. It's just compute the squares of the differences, sum across all the points, divide by n if you want. It's not very important. Depends on, because you're going to need essentially to minimize this. And this goes by different names in the different literatures. So in machine learning, this is typically called empirical risk. In statistics, it's called RSS, or residual sum of squares. It doesn't really matter what it's called. And so empirical risk minimization, which is now you're going to solve this problem of minimizing this function with respect to W0 and W and vector W, which you can call it empirical risk minimization or least squares, because it's essentially just minimizing the sum of squares, or empirical risk minimization with minimize. It's always the same. It's all the same function. It's just different names. Okay, so this is linear regression. So you may also, if you're more statistically oriented, you may ask, okay, but I have a good reason why I use a squared error loss. Okay, is because maybe I know that my data is contaminated by Gaussian noise. Okay, and I know that Gaussians have this quadratic thing up there, and that's actually the case. Okay, so from a statistical perspective, when you do standard linear regression, what you assume is the following: the inputs are deterministic; they're given. I'm not going to model the inputs. So I have a training set. The X values are given, but I don't know if they were generated or how they were generated. I don't care. They are given and fixed. Okay. And I assume that in my training set, the response for each example is independent from the other responses, given the corresponding input. So these yi's are independent of each other, given the corresponding xi's. Okay, so it's called conditional independence. Okay, and if we assume the following, there is a true clean value under there, which is actually this. It's W0 plus W transpose Xi. So it's what the linear predictor would give you. And what you are observing is a noisy version of these. So your Yi's are noisy versions of this clean value plus some noise. And the noise is Gaussian with zero mean and some variance sigma 2. There's lots of good arguments for using Gaussians. Maybe it's a sum of many different perturbations, and you invoke the central limit theorem and you say everything that you don't really know where it came from, it's sort of Gaussian. And it's a simple model. And if you do this, so what you immediately know that the density, I'm assuming that you know about Gaussians, okay? This was 7 years ago, I gave a prior lecture on probability stuff, but now I'm assuming you know what a Gaussian is. So the conditional density of the observation given the input is just a Gaussian with the clean value as the mean and the variance, which is sigma 2. And you may ask, but I don't know the variance. Do I need to know the variance? No, you don't need to know the variance. It will get the same thing. So the likelihood function, because of the independence assumption, is just a product of all the likelihood functions. You compute the product across the whole data set. And of course, in the likelihood function, these guys are fixed, right? These are fixed. These are observed. And you want to estimate maybe the 3 of these, or maybe you don't really need to estimate sigma 2. Okay? And then you write these. You know how to write the joint distribution of all the observations given the inputs. Okay? Then you can, the standard thing, this is very standard in statistics, it's like statistics 101. You apply logs. Log is very important because it transforms product into a sum. And the log of a Gaussian, so you all know, I guess, that how a Gaussian looks like, exponential of minus a square up there. And when you take the log of an exponential, the exponential just disappears. You just skip the exponent, and the exponent is a square. Okay, that looks like this. And so you have some constant that comes from the other stuff in the Gaussian, plus that term. But that term looks exactly like the empirical risk minimization thing that we had. It's a sum of squares, of errors. Remember that this is just what we were calling y hat, I. And so it's exactly the same. So when you're doing least squares estimation or empirical risk minimization or residual sum of squares minimization, you're doing maximum likelihood estimation under the assumption that your data is contaminated by Gaussian noise. So that is underlying justification. And then if you do least squares regression and you find out that your result is not being good, one of the reasons may be that this is a wrong assumption. Maybe you have outliers in the data. If the data has some spurious values which are very far away, then the Gaussian model is not a good model. And you need to use more sophisticated regression techniques such as robust regression. Maybe one thing that can be done is instead of using squared of the error, you can use the absolute value of the error, which is less sensitive to these spurious values because it doesn't grow so fast. So quadratics grow very fast. Linear functions don't grow so fast. Okay? So if you don't really understand, don't know much about likelihood functions and Gaussians and stuff, this is not very important. It is important, but it's not crucial for understanding what comes next. So another picture that I really like, and I think it shows kind of intuitively what linear regression is doing now in the two-dimensional case. I have all these data points. So the positions of the data points in the horizontal plane are the xi. So the position of each of these points in this plane are what I'm calling the xi's. And the vertical position of the points, so the vertical axis is the response, okay? And the linear function or an affine function, now in this case from R2 to R, from 2 dimensions to 1 dimension, a prediction, is like an infinitely hard plane of steel or some very infinitely hard object of steel, a sheet of steel or something like that. And imagine that you have these springs or these elastic bands that attach to each of the points and to this steel plane. And the position of the steel plane is the thing that minimizes the sum of the squares of the differences, of the distances between the points and the plane. Because the energy stored in an elastic band is proportional to the square of the elongation. And so that's the minimum energy position. So there's a physical interpretation for least squares regression, which I think kind of gives an intuition of what we're doing. It's just a physical intuition. I like physical intuitions, maybe you don't. And this is a picture from a classical book in statistical learning, which is called The Element of Statistical Learning, Haystadeep Shirani Friedman. It's not a great book, but it has very nice pictures. Okay. So one very important thing, it's a great book. I'd say it's a bit outdated. So how do you get one very important thing that people try to do? This is just kind of a practicality, is getting rid of this offset, getting rid of W0. Okay, because it's not so nice to have W0 plus this blah blah blah. Let's try to get rid of W0. One way we can use to get rid of W0 is to actually invent another feature, which is always 1. So you have your feature vector x1 to xp. So for each xi has p components, and we'll add an extra component, could be the first or the last or whatever you want to put it, doesn't matter. And then w is now a p plus 1 dimensional vector, which has w0 as a first component. So it has a 1 extra component. And so you can write this w0 plus the inner product simply as w times x now, because the first term of the inner product is going to be 1 times w0. And so you can just put everything in the same inner product, and you get rid of w0. There are other ways to get rid of w0, like normalizing the date and stuff, but I won't go into those. So essentially what I'll do from now on is I'll mostly ignore w0. Okay, we can do it like this, just assume that it's in there somehow, or that it was dealt with in some other way, because I don't want to carry this w0 around, because it's a bit annoying. Okay, let's see how we can solve linear regression. Maybe you've all seen this before, maybe not. So as we've seen, least squares, so you need to minimize with respect to this w now, the sum of the squares of the errors. So this is now, this guy here is y at I, and you need to compute the error, square it, and minimize the sum. And this can be written in a compact vector notation. So if you create a vector y on the right, which contains all the responses in the training set, n of them, and you create this matrix which contains at each row one of the xi's with its p components. So I take each xi, I transpose it, make it into a row, and stack them all. So I have this big matrix which has n rows, where n is the number of samples, times p columns, where p is the dimension of the feature vector and of the weight vector w, I'm sorry. And this is called the design matrix. This name design matrix comes from statistics, because why is it called design, you may wonder. Where is the design? Because it's when you're doing a statistical experiment, the creation of this matrix is where in my feature space should I get samples from? You're designing the experiment. So this matrix is called design matrix because it's where you design your experiment. It's where you choose the points for which you want the responses. It's kind of a bit outdated name, but it's for many machine learning applications, you just given whatever. But you don't design this matrix, but the name stuck, and it's still called the design matrix. Of course, now I'm assuming that you know your basic linear algebra. I'm assuming that you know how to compute the gradient of a quadratic form. Okay, if you don't worry, it's very easy to find out. So I'm assuming that you do. So you have a quadratic form up there, you need to minimize it. How do we minimize functions? We compute gradients and then set the gradient to 0. And so when you compute the gradient of a quadratic thing, in this case, you get this linear expression there. It's 2x transpose xw minus 1. Okay, so it's just, there's many ways of computing this gradient. One of them is to starting by writing this quadratic form up there, as noticing that the squared norm of any vector can be written as vector transpose itself. And then so we expand this quadratic form as y minus xw transpose y minus xw. Then you expand these and you have 4 terms, actually 3 terms. And then you compute the gradient of each of them. And when you do that, you get this expression down there. Okay? And so when you have the gradient, the problem is basically solved, or half solved, because now all you have to do is equate the gradient to 0. So here's the equation that you need to solve. You need to solve the gradient equal to 0 to find the minimum. Of course, I need to argue, you may ask, how is this enough to find a minimum? Well, yes, because this function is convex, so you kind of guess I think you know what a convex function is. We will come back to this later on. Convex function that does not have local minima. So if you find a zero of the derivative, a zero of the gradient, you know it's a minimum. So all you have to do is solve this equation, which asks you for the gradient to be equal to zero. So you need to find a solution with respect to W. This is what this notation means. You want a solution with respect to W of this equation. And this equation can be written as xt x w equals xty, right? I'm moving xty to the right-hand side. And this is just a linear system. It's some matrix, let's say A times an unknown w equals some b, right? And the way to solve a linear system is, if you can, you invert the matrix and you say, okay, w is just a minus 1 b. Okay, so that's how you solve a linear system. And this is just a linear system, so my matrix A is x transpose x, and my vector B is x transpose y. And so this is the solution, x transpose x minus 1, so inverse of x transpose x, x transpose y. And notice that this matrix here is a P by P matrix. It has the same dimension as W, or as the feature vectors x. Now you may ask, how do you know that this matrix is invertible? I don't, okay? So this needs to have this caveat, which is this is possible if x transpose x is invertible. Otherwise, it's not possible, okay? For those of you who know more of linear algebra, this means that I need the rank of x to be P. I cannot have a matrix x that has a rank lower than P, which requires at least that n is larger or equal than P, because as some of you will know, the rank of a matrix, the rank of this matrix is less or equal than the minimum of P and N. So the rank of a matrix is less or equal than the smallest of the dimensions. It cannot be bigger than the smallest of the dimensions. And having a matrix with rank less than P in this kind of matrix, so the matrix has P columns. Let's assume that N is big, so that's not a problem. If you have having rank less than P, it means that two of the columns, for example, are collinear, or that some columns are dependent on each other. They're not P independent columns, which means that you have a feature that's redundant. If you have a feature that's redundant, that depends on the other features exactly, then the problem has no solution. It has infinitely many solutions because you have an underdetermined system. Okay, so this is linear regression 101. How do you assess the quality? So the typical thing that people use, and that is really reported in studies, even in the public, for public media, for popular media about statistical stuff, you see very often this coefficient of determination, which essentially goes like this. You have your data, and you take only the responses, and you compute the total sum squared. That's a sort of the variance of the responses multiplied by n. So you take the average, you take each sample and you subtract the average, you square, you sum across all the data points. That's the total sum of squares. I'll have a picture for you what this means. And then you take also the sum of the squared residuals, which is once you estimate the model has some final residuals, which are the differences between the estimated values and the observed values. And this is called the sum of residuals, okay? And the coefficient of determination is given by 1 minus the ratio between these two things. You see, if SSR is much smaller than TSS, if the sum of squared residuals is much smaller than the total sum of squares, then the second number is much less than 1, much smaller than 1, and R2 is very large, which is good, okay? Why is it good? This is the picture, okay? So the total, you can think of the total sum of squares as the following way. So this thing here, okay, this vertical here, is the difference between yi, 1yi, and y bar. Y bar is the average of the y's, okay? So when you square it, what happens when you square it? It's like computing the area of a square. And that pink square, those pink square there's are the area, each of these squares is the area of each of these little squares. So you sum these areas of these squares, you get the total sum of squares. Now you repeat the same operation, but after fitting your linear regression. You take the residuals, you square them, so you're computing the area of these little blue squares. So these little blue squares are these guys here, okay? And now, for example, in this case, the SSR, the sum of squared residuals, it's much smaller than the total sum of squares, which means that you've done a good job. So regression is meaningful. It has a very high R2. Okay, so this is important to know if you're dealing with linear regression. And again, I like this another XKCD cartoon about R2. If you have this plot and you did some linear regression, your R2 is 0.06, which is very low. And then on the other, you can draw this constellation. And so the comment is, I don't trust linear regression when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations on it. So it's important to keep an eye on R2 if you're doing regression for some scientific purpose to understand something. Okay, so a couple of slides on the geometry of linear regression, which will be important later on. So what do we mean by y hat? So I mean y hat is the predicted points, is the predicted values at the sample points. It's very easy to explain in a plot what this means. So you have some random points, some training points. You fit a line. There you go. Okay, and then this. Let's say that this point here. This point here is some yi. This point here on the line, exactly on the same vertical, is what we're calling yi hat. So it's the predicted value for the same x that's being predicted by the regression function in that same position. Okay, and it's easy because we now have w, and our model is that clean values are just x times w. It's just now I take x multiplied by the least squares estimate of w, and we just need to plug in these. We know that this part here is what we had. It's w hat least squared. We just multiply by x, and we get this matrix which is called P typically, and it's called the hat matrix. And the reason that's given in the Hayes-Friedman for why this is called the hat matrix, it's because it's the matrix that puts the hat on y. So you go from y to y hat by using P. So it's the matrix that puts the hat on y. And this matrix is a projection matrix. It's an idempotent matrix. I guess some of you will know what it means. So idempotent means that if you multiply a matrix by itself, you get back the same matrix. That's what happens when you project something. If I project a point on the wall, and then I take the projection and project it on the wall again, it doesn't move because it's already on the wall. So it's when you projection operators are idempotent. You don't need to apply them twice because once it's applied, nothing happens from there. And it's easy. Just a trivial exercise in linear algebra. Just has this huge train of matrices and transposes and inverses, and everything cancels out, and you just get P back. When you start with P times P, you get P at the other end. And it has a nice interpretation because we can see that Py, okay, P times Y, which is this Y hat, is, as we saw, X times least squares, and we know what least squares means. Least squares means the minimizer of this problem. And now you can move this X inside this minimization, and we notice that what is exactly doing is finding, so this vector Y hat, these predicted values, is the projection of my observation vector y into the range space of x. Because what we know is that y hat, because of its form, so anything that if you take some matrix x and you multiply by some vector, say alpha, the result is a linear combination of the columns of x, as you know from your basic linear algebra, right? You have a matrix multiplied by a vector. You're basically computing linear combination of the columns of the matrix using as weights the vector, which means that my y hat is always a linear combination of columns of x. And so what y hat is the vector in the linear combination space of the columns of x, called the range of x, that is as close as possible to the original y's. Okay, so this is it's orthogonal projection. So in pictures, this is what we have. So this picture is in Rn, because suppose I have n samples. So in this case, we have 3 samples. Okay, because it's in R3, it's a 3-dimensional picture. Y is the 3 components of y, the 3 coordinates of y are the 3 observations, y1, y2, y3. Okay, but I have a design matrix with only 2 columns, okay, which are written down here. It's this horizontal space down here, x1 and x2. x1 and x2 are the columns of matrix X, okay? And when you compute the residual, when you compute the projection, you're basically looking for what is the closest vector to Y, what is the closest vector in the range, which can be written as a linear combination of these two vectors, x1 and x2, that is as close as possible to Y, and it's a orthogonal projection. Okay, this is good to know. It's not crucial for what comes next, but it's interesting to know. Okay, so how do we move on to nonlinear situations where you know that it doesn't make sense to do linear regression because your dependency is not linear. So the classical thing is to replace your original X by some functions of X. Okay, so you take your original X and you compute a collection of functions of X. Typically, we take the opportunity to inject in there one of them being equal to 1 to get rid of W0. So one of them is just 1. It's a constant. And the others are whatever functions you want to compute of X, okay? Or learn, okay? These components are typically called features. Phi is typically called a feature map, okay? And it could be, for example, this could be a big, deep network that you don't care what's in there. There's some object that's the input, some image or whatever. And then there's a network that does whatever it does. And in the end, you have some collection of D, actually D minus 1, actually D, weights, W0. There's a bias term there because you have this one here. This is the one that's there. And then you have these final weights. Okay, so you can think of a big neural network as something that computes features from some object X. Okay, and it computes how many? D minus 1 of them, where that D minus 1 is the dimension of the final layer. Okay, if you're doing regression. So it could be this. Or more classically, it could be something else, which we'll see in a second. But nothing changes. This is what really matters. From a linear regression perspective, nothing at all changes. Okay, so your least squares criterion now becomes this. So the prediction is no longer just W transpose X. Now it becomes W transpose phi of X because you're not dealing with X itself, but with its transformation. So the prediction now is here. This is Y hat Y. And you have the square of the difference. And so you can rewrite it again exactly in the same form with this matrix vector formulation, just by redefining what the design matrix is now. Instead of the design matrix containing the components of X itself, it contains the features of X itself, okay? And this is, you recover the previous case if the features are just the components. If phi 0 is 1 and phi 1 is x1, and phi 2 is x2, if you recover just the features, then you recover the classical case, but it contains many other things depending on what functions you put in there. Okay? Classical example is if you want to fit a polynomial just in one dimension, if you want to fit, say, a cubic function to data, the way to do it is to do this transformation, which takes some number, this is just in one dimension, and computes some powers of that number. Say power 0, which gives you the 1, x squared up to some order. Okay, now if you replace your x by this little vector, and you formulate this problem as linear regression, you're doing polynomial regression. Or you can do it in R2, say order k polynomial in R2. You need to expand, so little x now has two numbers, x1 and x2. And to do polynomial expansion, you need to expand this little vector into a big vector that contains all the monomials of order up to some order. So for example, 1, x1, x2, x1 squared, x1, x2, x2 squared. Then if you go all the way up to polynomials of order 3, you need to have x1 to the third power, x1 times x2 squared, x2 times x1 squared, x1, x2, no, that's enough. No, I added to mine. All the way to some power, okay? And if you want to do it in RP, then you can consider a vector that has all the monomials of degree up to k, which of course belongs to some RD, and D is a very big number. Okay, the way it grows is that if you're doing polynomial regression in RP, this grows exponentially with the order of the polynomial. So no one does this. No one uses these, except if you are in very, very low dimensions. No one does polynomial regression in high dimensions. Other types of linear regression, which are much more used are radial basis functions. We still use some, they are somehow connected to deep learning and to deep networks. So in radial basis functions, what the functions that you use to become nonlinear have this form, which they are some function of the distance between your point X and some center C. I'll show you a picture in a second. So you have fixed centers. So you have something like this. So if you're doing regression in one dimension, each of these functions will be something like this. A Gaussian, a Gaussian, a Gaussian, a Gaussian, a Gaussian, a Gaussian, where each of these points is one of those CJs. This is CJ, this is CJ plus 1, and so on. Okay? You just have a bunch of functions that are fixed, okay? And for a given point, okay, the point computes a lot of features, which is some function computed as the distance, how far this point is to each of these so-called centers. And this function phi could be Gaussian, that's what I used in the picture. It could be many other things. There's also splines. There's huge literature on splines for regression. Let me show you a picture. So if you're doing Gaussian radial basis function regression, for example, this is the blue dots are your samples. The other lines are these Gaussian functions located at different centers, weighted, multiplied by some weights, and the function that you get, so the regression function is this function that runs here in the middle of the point. It's not very visible. Okay, so see, you're doing nonlinear regression. This is extremely nonlinear, right? It's not linear at all. It's just this function that goes up and down with a bump, 2 bumps. But you're solving a linear regression problem because the problem that you solve has the same form as before exactly. You need to set up the design matrix, and then you need to compute X transpose X, invert it, and it's done. Okay, so it's a very simple problem. What you cannot do when it becomes nonlinear, and it becomes much harder, is if you don't have fixed centers. If you also want to estimate the centers, then everything becomes a lot more complicated. Okay, so you can do linear regression, nonlinear regression, as if it was linear regression, because the linear adjective, the important part is not linearity with respect to the input, it's linearity with respect to the weights, to the parameters. That's what the linear part is important. You can do it as long as the functions that you use to do this expansion, these 5 functions, are fixed. If you want to learn these functions, that's a whole different story. That's learning representations, that's deep learning, that's another story. Okay, for linear models, we assume that these functions are fixed. Okay, ridge regression. We use these every day. If you've ever trained a neural network, you've used weight decay, you've used this. So what happens if the rank of X is less than P? For example, if you don't have enough data, if your parameter vector has dimension 20 and you only have 15 points, okay, what happens? You cannot compute least square solution because this matrix, this inversion does not exist because the matrix has rank less than P, okay? This is equivalent to trying to solve a problem that looks like this. So you have this, your system matrix is like this. You have, this is X, these are your weights, okay? These are your observation, this is Y. This is like a linear system where you have fewer equations than unknowns. You have more unknowns. You have W, P unknowns, only N equations, and then it's less than P, you cannot solve this problem, okay? You can't even solve the least squares problem in this case, okay? You will see why, because there are many solutions. We'll see that in a second. So what is typically done to solve this is, okay, let's try to make it solvable by adding this extra term here, which is penalizing the square of the norm of W. Okay, you're preventing W from becoming too large. So let me try to explain why this kind of makes sense. If this problem that you're trying to solve here is this Y and XW, okay, is such that as I showed in the picture, where Y looks like this, Y, let me write Y equals X looks like this, and W looks like this, okay? This is, if you could solve this system, then the minimization is 0, because you can get some W that gets you W, X times W equal Y, so you get zero error. The problem is that this solution is not unique, because this is a problem with fewer equations than unknowns. So there are many solutions, okay? It's not an impossible system, it's an underdetermined system because you have fewer equations than unknowns. And so there are many, notice that you're trying to write a vector that has dimension n as a linear combination of vectors of dimension n, but you have more than n of them. So there are many ways in which you can solve this problem. There are infinitely many solutions, okay? And some solutions may go toward infinity because it doesn't matter. You can, if you have to imagine that you have two of these columns, one is the symmetric of the other. You can multiply one of them by 7 and the other one by -7. They cancel out, gives you a 0. But you can multiply by 7 million and -7 million, and it's still 0. So this redundancy is what causes the problem. And so you can try to solve it by stopping the components of W from growing unbounded by forcing them to be inside this term, which is called the ridge regression term, by adding the square of the norm, okay? And again, I'm not gonna do the details. If you want to solve this problem, you do the same technique, compute the gradient of the square of the norm is trivial, it's just 2 times W, and you end up with this linear system of equations that you need to solve. And now, this always has a solution, because X transpose X, for those of you who know your linear algebra, X transpose X is obviously positive semi-definite. It has no negative eigenvalues. It may have 0 eigenvalues, but doesn't have any negative eigenvalues. If you multiply, remember what a positive semi-definite matrix is. Who knows what a positive semi-definite matrix is? Well, I'm sure you all, most of you know, right? Who doesn't know what a positive semi-definite matrix is? Who doesn't? You're too shy. Okay, yeah. It's the only brave guy. Okay, so positive semi-definite matrix is a matrix that if you compute the quadratic form using this vector, and this means sum across all i's and all j's of vi, vj, aij, is what this thing on the left means. For any vector that you want to put in there, you always get a number which is larger or equal than 0. This is what's called a PSD matrix. It's not the Portuguese, the Social Democratic Party is a positive semi-definite. Okay, this is what a positive semi-definite means. And it's obvious that this matrix here is positive definite, because in addition to, if you compute the quadratic form with this matrix, you get 2 terms. You get, well, first of all, it's obvious that V transpose X transpose XV is positive. Why? Because you can write this as XV transpose times XV, and this is just norm squared of XV, and the norm squared is, of course, larger or equal than 0, because it's a norm squared. So this matrix X transpose X is positive semi-definite. Now, the other one, it's just identity. And identity is just, if you compute identity, V transpose identity V is just V transpose V, and V transpose V is just norm V squared. Okay? And this is, of course, larger or equal than 0. Actually, for any lambda, this is larger than 0, unless V is 0. Okay? It's positive it's positive definite, not positive semi-definite. This one is positive definite. So positive definite matrix is a matrix that this quadratic form is always larger than 0, except if V is 0. Okay? Of course, if V is 0, this is 0. Okay? And so what, in practical terms, what adding this lambda I matrix there, which is the consequence of adding these, this is exactly why this is added, is that you transform a matrix that is positive semi-definite, but may have 0 eigenvalues, it may be non-invertible, into one that is necessarily invertible, no matter what, as long as lambda is larger than 0. So you transform a non-invertible matrix into an invertible matrix. And this can be seen as a Bayesian estimate of, if you know what this is, as with a Gaussian prior with that covariance. So this technique goes by many, many other names. This has been used in many areas, and it's called, modernly in machine learning, it's called weight decay. It's exactly this. It's called penalized least squares in statistics. It's called Tikhonov regularization in inverse problems. It's called L2 regularization in statistics too. It's there are more names, but it's always, every time you have some function that you need to solve, okay, and there's problems with the solution of these, and you add this term to help you solve the problem. This has been used in many different areas, and it has different names. It was reinvented dozens of times in different areas, but it's always the same. Now, in practice, it may be the case that even if least squares exist and it can be computed, maybe ridge may be preferable. Maybe the total mean squared error at the end is lower. But this is just an example, an illustration of that. Suppose that you're fitting. I think this example is from Kevin Murphy's book. I'm almost sure it is. I should have written it there. You're fitting an order 14 polynomial to 21 points. This is pretty dangerous, right? If you have only 21 points, a 14-dimensional polynomial is pretty high. So it's probably going to be a bit bumpy. And it is a bit bumpy if you do the least squares regression. This is not exactly with least squares. This is with, what's written in there is that log, or natural logarithm, log of lambda is around -20. So it's really, really small lambda. It's almost like there is no lambda at all. So it's basically least squares. And you get this bumpy estimate because the order of polynomial is probably too high. And this is in this lower plot is log of lambda is approximately -8. So it's a much bigger lambda, and you get a much smoother line, okay? Because you're forcing the coefficient of the polynomial to have a smaller norm, okay, smaller squared norm. And on the right side, what we have is the blue line. The blue line is the residual sum of squares at the estimate. So you, of course, if you fit, and if you the lower lambda is, the lower the error in the fit, because you're allowing the polynomial to go closer to the points, okay? But then if you resample other points from the same underlying function, which in this case I don't know what it is, and you check the error, which is what is being here called test MSE, okay? If you compute the test MSE, you see that the minimum is obtained roughly around here, which is not for 0 lambda. Even if, although the least square solution, strictly speaking, exists, it's not the best one in the mean squared sense, because if you can try it on other data from the same function and check that it's not, it's better to always regularize a little bit, okay? We'll come back to this a bit more formally later, okay? So now this kind of suggests that we talk about something which is called the bias-variance decomposition, and I will illustrate it with only in one-dimensional case. What is the bias-variance decomposition? Well, the bias-variance decomposition is a very simple concept, which is based on the fact that I assume you all know, which is this equality up there, that the variance of some variable is the expected value of the square minus the square of the expected value. You've learned this in probability 101, probability and statistics. Now, if you apply these to the mean squared error, so mean squared error is the expected value of the difference between the true W and the estimated W. Okay, so this is the true W. This is the estimated W. This is the difference of the square of the difference. I'm using P equals 1, so I'm estimating only one W. It's just one line with, I'm only estimating the slope, that's all. Okay, and note the variance. So this is the variance. The variance would be something like what I have here. Well, I'm rewriting this thing up here as E of U squared equals variance of U plus E of U squared, okay? So the expected value of the square can be decomposed in the variance plus the square of the expected value. That's what the expression up there means. And if you apply this to the error, to the so-called mean squared error, so this would be take the place of the mean squared error, you get this decomposition. It says the variance is whatever the variance is, and the other one is the square bias. Square bias is the expected value. So you don't squaring inside, you're squaring outside. So the expected value before you square it on the right side here is just the expected value of the difference between the true value W and its estimate, okay? And now if we do ridge regression and you plot these two quantities, this is what a typical thing looks like. So the top line is the mean squared error of least squares. If lambda is 0, which is what you have, it's here, it's these starting points. It's there just for reference, okay? And then as lambda increases, the bias goes up. And I'll show you in a second why. Because your function, if you think of a polynomial, is getting stiffer and stiffer, and it cannot wiggle so much around, and the variance is coming down, okay? And the sum of the two will give you the mean squared error. And the mean squared error has this sweet spot somewhere in the middle, where the variance is not too high, the bias squared is also not too high yet, and the sum of the two is the minimizer. And this is somewhere here. For this example, it would be lambda equals 1. This is a very toy example, okay? And what does this look like when you're estimating functions, okay? It looks sort of like this. Suppose you have these, this is a picture by a nice course on machine learning by Sebastian Rashka from Wisconsin. So suppose you're estimating the true function is this quadratic thing with a gray line, okay? And you have 3 training sets, all sampled from this gray line, the blues, the greens, and the yellows, okay? And now you're estimating just the order 1 polynomial, which is just a straight line, okay? The line is extremely stable. No matter what training set you use, the line is almost always the same. But the line is very different from the underlying function. So there's a very low variance because the line doesn't change too much from data set to data set. But it's very wrong in the sense that this difference is always big. The difference between what you estimate and the true line is very big. Okay, so this is a situation of high bias, low variance, but the function doesn't change much. So it doesn't wiggle too much, so the variance is low. On the other hand, if you use a very complex approximation, so in this case, it's not a polynomial, it's like a piecewise linear interpolation, okay? You take your training set and you just join the points by straight lines. That's a function, okay? But the function has a very low bias because it's never very far away from the true function, okay? But it changes a lot from data set to data set because if you change the data set, if you move from the blues to the yellows, the function changes a lot. So the function wiggles a lot depending on the training set, okay? So this is a situation on the right of low bias because in expectation, if you average the functions for the different data sets, in expectation, it's always very close to the gray line, okay? But they change a lot. There's a big uncertainty region around these functions. So in practice, how do you choose and then we stop? How do you choose lambda or the complexity of the model or whatever? So one of the techniques that's classically used is something called cross-validation, which goes like this. So you have your available data, x1 and y1 to xn and yn. You divide it into k disjoint subsets. So you split these into k, sometimes called folds. Each one of them, if you have k of them and they're disjoint, each one of them will have n over k samples. And let's call these samples, these subsets, S1 to Sk. Now, for each one of them, you learn the function from all the samples not in Sk. So you take, suppose you are doing 10-fold, okay? You have 10-fold, you have 1,000 points, you have 10-fold, you take the first 100 points, and you learn your model on the remaining 900, okay? And then you test it, you assess it, its mean squared error, on the ones that you left out, on the first 100, okay? And now you repeat these 10 times. You leave out the second 100, and you train the model from the first 100 and the others from 200 to the 5. So you're always learning on 900 and testing on 100. And you do these 10 times in this case, in this example that I was giving, okay? And then in the end, you just average the errors that you got from these folds, which is it's the average across all the folds of the estimates of the mean squared error for each of the folds. All of them are a function of whatever you use for your regularization parameter. And then you just choose lambda. So typical numbers be 5 or 10. You just choose lambda by minimizing this estimate of your mean squared error obtained by training on a subset of the data, which is typically a large fraction, testing on a small fraction, and then repeating these several times by leaving out different. There's an extreme case of these, which is called LUUCV, which stands for leave one out cross-validation, where you do these where k is equal to n. You leave only one point out, and you train on all the others, and you check the error on that first point, and then you do that for the second point, and for the third point, and for the fourth point, and you do that for all the points. This is extremely expensive because you need to run your learning method as many times as point you have. So unfortunately, for linear, I'm not going to that, but it's an interesting fact. For linear regression, there is a closed form expression for the leave one out error without having to repeat the method n times. Okay, there's a very elegant linear algebra result that allows you to compute the leave one out the leave one out error without having to repeat the procedure, just by learning once. It's very elegant. I will not go into that. Extreme case that I was saying, leave one out. I forgot it was there. And this is a picture that illustrates. So you learn on the white part, you test on the other one, you repeat these as many times, you average the errors. And you can do this not only for regression, you can do it for classification problem, for whatever problem. This is a very commonly used technique to do fine-tuning of things. Okay, let's stop now. It's about time for coffee break. Okay? And you'll be back at what time? 11? 11, yeah. Okay, that's the request. Oh, sorry, are there any questions? I'll be around during coffee break, yeah. Of course. Okay. It's not raining, I was just kidding. And don't forget, this afternoon you have the lab session starting at 2, a location, so you'll just follow the monitors, we'll show you around. And then there'll be the welcome reception at 5. At the outside of this building, as you go out of the building through the front door, it's just in front of you, slightly to the left. You see some pine trees, big pine trees. It's below those pine trees under the shade. Okay? Why this is so annoyingly making sound here? Okay, it's okay. You can't hear this sound, do you? Can you? No. Okay, let's go on. So, as I always have these existential doubts about giving this lecture about linear regression and linear classification these days. So I asked, I have something like this later on, but I asked like 5 minutes ago, I asked Gemini 2.5 Pro, which is supposed to be the most knowledgeable entity in the world. And I asked, in this day and age of deep learning, does it still make sense to know and to learn the basics of linear regression and linear classification? And Gemini asks, yes, understanding the basics of linear regression and linear classification is absolutely essential and non-negotiable for anyone learning machine learning. So that made me feel better. These models are the foundational pillars upon which more complex and powerful methods, including deep learning, are built. Skipping them would be like trying to understand calculus without first learning algebra. So that's good. This is really loud now. Can't you hear it? Yeah, it's off, I think. But it's muted. Okay, I'll try to. Okay. Okay, so we just finished tenfold CV and cross-validation for linear regression. So now I'll probably show you something which maybe those of you who already took a basic machine learning course and studied linear regression may not have seen. And I think which is an interesting view also, which is just for something slightly different, but it opens the door to very important observations. So you remember that we saw it a while ago that we can write, so that's the linear system that you need to solve when you're solving ridge regression. Once we add this little term here to invert this matrix. Remember that the ridge regression was x transpose x plus lambda I inverse multiplied by that. And so by just slightly manipulating this equation, we can write it as it's on the right. So W ridge, it's just a very small manipulation of these where you multiply, you leave these lambda Wi on one side, and you multiply everything by 1 over lambda, and you move the other parts to the other side. It's just the equivalent equations, okay? Why is this is a trivial observation. Why is this important or relevant? Because it shows that your estimate in ridge regression, and it's the same for a linear regression without ridge, because it's just a particular case when lambda is 0, that the W hat that you get from ridge regression is of the form x transpose times some vector, alpha. And we can write alpha, it looks like that. It looks like it's circular in the sense that, well, but alpha itself depends on W hat ridge. Forget about that. What really matters is that it has this form. And what this shows is that W is a linear combination of the columns of X transpose, okay? Which is because X transpose is instead of what were the rows of X, now are the columns of X transpose and vice versa, right? You transpose the matrix. And this is a very important observation because it shows that your weight vector is necessarily a linear combination of the rows of X. And what are the rows of X? The rows of X are the Xi's. So remember that matrix X, the design matrix, its rows were X1 transpose, X2 transpose, Xn transpose, where each of these is one of the samples in the training set. Okay, this is a very interesting and very important observation that your weight estimate is a linear combination of the points that you observed, for sure, because of this relationship. Of course, you need to find out what the weights are, the alphas, but this is already clearly true. Okay, which means that when you need to compute some predicted value, how do you compute predicted value? Predicted value, take W. So predicted value for some new point is y hat at some new point, say x star, is just W transpose inner product with x star, well, x star above. Okay, if you want a prediction in some point, of course, what you need to do is take W and compute the inner product with x, with the new point. But because W is a linear combination of x's, and the inner product is linear, so inner product with a linear combination is a linear combination of the inner products. Okay, we can notice that the prediction of y hat at some new point x, which is x transpose times W, can be written as a linear combination of inner products of the new x with all the points in the training set. Okay, so one way of seeing the estimate of some new point is that you take your new point x, compute inner product with all the points in the training set, and now you weight these inner products according to these weights alpha, which I haven't told you how to find yet, and that's the prediction. Okay, which makes a lot of sense because it means that the points that are the xi's that are close to your x will provide good estimates of what the response will be. The response for those points will be probably very close to the responses for those points, okay? Because the points are nearby, sort of a kind of a nearest neighbor kind of reasoning. And how do we find alpha? So we just noticed that we could write W hat reach as X transpose alpha, and alpha has a closed form, it's that. Okay, so it was that. It was just a simple manipulation of the first equation. And if you just plug in the second equation, where you have W reach on that right side, if you plug in this equality in there, you get an equation that depends only on alpha, just alpha equals blah, blah, blah. You can solve it, and you get this expression, which is alpha equals 1 over lambda, y minus x transpose alpha. Because alpha is in both sides, you need to move alpha to the other side, and then you have an inversion, and you get alpha equals lambda I plus x transpose minus 1 y. And this is similar in a sense to the least squares regression, where you had x transpose x, and now you have x transpose. Remember that x transpose x is p by p, and x transpose is n by n. So you have two different matrices which you may want to choose to invert to find, because if you know alpha, you know W, because once you know alpha, if you know alpha, you know W. You can estimate W directly using W equals X transpose X plus lambda I minus 1 X transpose Y, or in this way. And they're equivalent, they're the same, of course, because this is just identities, algebraic identities. Okay? When should you choose? So you can have the direct expression that I just said. So W reach can be written like these, which we just saw, X transpose, and then you plug in alpha. Or in the one expression that you were seeing before, which is X transpose X, and they're both the same. Okay, so you can have either an n times n inversion or a p by p inversion. Which one should you choose? Because you know computing matrix inversion is expensive. Which one should you choose? The smallest one, that's the smallest matrix. So if you have less, if n is smaller than p, which is in the case where you're forced to use regression, you have fewer data points than the dimension of p, you choose the one on the left. If you have small p and big N, standard classical statistics scenario, you choose the one on the right. But they're equivalent. They lead to the same solution. But keep in mind that inverting a matrix costs of the order of I don't want to say n because I'm using n, an m by m matrix. You have an m by m matrix. Cost of inverting a matrix is approximately cubic in the size of the matrix. So it's very important that you always try to avoid inverting matrices, especially if they're big. And if you can choose a smaller matrix, you should. Okay. Now, this matrix X transpose is actually a well-known matrix in the field of machine learning, which is called the Gram matrix. If you notice carefully, X transpose is of the form, so it's like this. So what do you do? So each row of the matrix is a point in the training set, x1, x2, up to xn. And so the transpose is here, these are the points. And so when you're multiplying one by the other, you're computing inner products between a point and another point, a point and another point, okay? So the elements of this matrix, X transpose, the element ij is just the inner product between point xi and point xj in the training set. And this is called the Gram matrix. If you ever studied kernel methods, you've seen these many times. And but if not, in modern machine learning courses that do not cover kernels, this is not very touched upon. And this is what actually opens the door to kernel methods, which are very important. So remember that now we have these expressions. So we can compute the prediction by computing a weighted average at some point x, the weighted average of the inner product of the point that for which I want to do the prediction with every point in the training set and then multiplying by these alphas. And I have a closed form expression for alpha. And to find this closed form expression for alpha, I need to invert the matrix, and the matrix has inside the Gram matrix. So all you need to do with x is the only operation that involves x's, that involve the x points, are inner product here, inner product there. So nothing else is, you don't need to do anything else with x other than inner products, okay? And so this is what I've written there. So data points are only involved via inner products, nowhere else. They don't appear anywhere else. And so it opens the door to a very easy way of doing nonlinear methods, because you can just replace a point by some feature transformations, a feature map phi. Okay, you go from RP to RD, as we saw before. And now if you're using this form, rather than inverting the matrix, the standard way we saw before, you can replace the inner product between the original points by the inner product after transformation, assuming that now you have another space where you can compute inner products, okay? And you still need to find alpha by solving that system, and that system involves this matrix, which is still the Gram matrix, but now instead of containing all the inner products between the points themselves, it contains all the inner products between the transformations of the points, okay? And so, of course, what happens when you do this nonlinear jump is that you move your inner products from RP, which is where X is used to live, to RD, which may be much higher dimensional. So you may be faced with the need to compute much higher dimensional inner products. Is that bad? Well, it turns out it's not bad. This is the topic of kernel methods, okay? And let me show you a very simple example just to motivate the idea. Suppose you want to do polynomial regression in R2, okay? So you take your point, each point is x1, x2, it has two components, and you compute all the second order, it could be actually all the zero first and second order expansion, but the simplest example is like this. So you compute the square of the first one, the square of the second one, and the product of both. So it's all monomials of order 0 and 2, okay? Now, if you want to compute the inner product between two of those vectors on the right, so these are 4-dimensional vectors, 1, 2, 3, 4 dimensions, and you want to compute the inner product between these two, say x and x prime, don't worry too much about it, just inner product between two vectors that look like these, one like this, another one like this, but with primes there, blah, 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 all the primes, you get this expansion. But if you look carefully at this expression, you notice that you can actually write it down as the square of the inner product in the lower dimension, only between x1 and x2, squared plus 1. So you actually can compute an inner product in dimension 4 just by computing the inner product in dimension 2 and then squaring it and adding 1. Okay, so you don't really need to go to the high dimension. You can do the things in the lower dimension. And when this is what I've just said, the inner product in R4 is just a function of the inner product in R2. And this is called the kernel. This is what's called the kernel. The kernel is a function between two objects that is equivalent to first computing some transformation of the objects and then computing the inner product in the transformed space. Okay? And this was, so kernel least squares regression what we need to do is, of course, where you had these inner products, now you're going to replace these by k of xi. That's all. Yeah, there you go. So it's called kernel least squares regression. You just, for a new point x, all you have to do is compute the kernel between x and all the points in the training set, multiplied by the corresponding alpha, and that's the prediction. And alpha can be found again by solving that problem there, where G, of course, now is the Gram matrix, but now the Gram matrix is just the kernel matrix computed for all the pairs of points. Okay, so this is kernel methods for regression in 3 slides, very simple. This is very, very powerful, and this was the deep learning of 20 years ago was kernel methods. Okay, in the early 2000s, late 90s, early 2000s, at the beginning, first decade of this century, like first 5 years, 50% of the papers in machine learning conferences were about kernels. Kernel this, kernel that. There were kernel versions of everything. So the trick was, take some known machine learning technique, PCA or Kalman filters or whatever, and massage it such that you can write it using only inner products. Okay? Sometimes you need to reframe the problem, and once it's written using only inner product, you take the inner product and replace by the kernels, and you make it completely arbitrarily nonlinear, depending on the kernel that you choose. Okay, so this was a very, very big trend. The thing is that it's not easy to learn the kernels, and so it's not a representation learning like in deep learning where you need to know the kernel, you need to design the kernel. And that's what made them be sort of surpassed in some way by deep learning. So just very briefly, kernel regression, it's still used in many contexts. So first of all, it's very important thing is that it starts with objects that do not need any structure. They don't need to have any structure at all. You can think of this set of objects as the set of people, the set of chairs, the set of anything. There's no mathematical properties that you need to invoke for X. It's just a set of things. Okay? As long as you can compute some kernel that takes a pair of things and produces a number. Okay? You need to define this function somehow. You can do it in whatever way you want. Okay? And I say that this function is a kernel if there is some function phi, such that computing the kernel is the same as computing this function phi and then computing the inner product. If you don't know what the Hilbert space is, it doesn't really matter. And now there's a very famous theorem which is central in this topic, which is a symmetric function. What's a symmetric function? A function that takes two objects and produces a number, a real number, such that it doesn't matter which order the objects have. So k of x1, x2 is the same as k x2, x1. So typically the kernel is seen as a measure of similarity, okay? How similar these two objects are. And I say that it's a kernel if and only if the Gram matrix is positive semi-definite. Take a collection of objects, compute all the kernels between all the pairs of objects, put it in a matrix. Is this matrix positive semi-definite? Yes. Then it's a kernel. You don't even need to know what this function is. You don't care. Okay? As long as you can show that there's this matrix this K that you built satisfies this property of always giving positive semi-definite Gram matrices, you know that this is true. There is some transformation that we are doing implicitly. Okay, but we don't need to worry about that. And so because G is PSD, because G is positive semi-definite, this matrix inversion always exists. And so the problem is well defined. I can solve it as long as I have a valid kernel. So there are many examples. I could go on now for an hour giving you examples of kernels. For example, linear transformations are a kernel, defined kernels. Polynomial transformation, defined kernels. So everything we've seen up to now in the polynomials, defined kernels of any order. Doesn't matter. These are all kernels. You can even have infinite dimensional transformations where you map from a point to a function. Okay, if you take a point and transform that point into a Gaussian function that has that point as the mean, that's a function. So it's an infinite dimensional representation of the point as a function. But you don't really care because the inner product between these two functions can be written very simply as just a Gaussian bit of the difference between the two. So RBFs that we saw a while ago are also kernels. Okay, radial basis function are also kernels. And the beauty is that you can build kernels for any type of object. So the kernel sort of encapsulates, it separates, it creates an interface between a learning algorithm and the representation of the object. You don't care what the object looks like. It can be a set, a string, an image, a graph, whatever. It doesn't really matter. Okay? And so there are many kernels for many different things. I don't want to spend too much time now on kernels. For sets, for strings, like 20-something years ago, it was a big rage that there was these kernel methods for NLP. It's all gone. It's not used anymore, not in this application. There are many, many other kernels. And so, as I like to do, I was having these doubts, and I went again to Gemini 2.5 Pro and asked, in the day and age of deep learning, for someone learning the foundations of machine learning, is it still worth to study kernels? And he did, when I asked this a while ago to some person here, it said, maybe it started talking about GPU kernels or something. No. He didn't. He understood what I was asking. And he said, absolutely. While deep learning gets the attention, studying kernels is a critical step for any serious ML student for 3 key reasons. It builds your foundation, so kernels are the clearest way to learn the trick of making linear models work on complex nonlinear data. The concept of transforming data to find patterns is the cornerstone of modern AI. It's a practical tool. For smaller data sets, kernel methods like support vector machines, which I will not talk about, are often faster, require less data, and can outperform massive deep learning models. And it unlocks deep learning theory. Okay, so kernels are used to explain how deep learning works. If you ever heard about or studied something called the neural tangent kernel, you've seen that you need to know what the kernel is to understand that kind of theory. So kernels provide a vital bridge to understanding neural networks. Modern research even shows that infinitely wide neural networks behave exactly like kernel machines, making kernels essential for grasping the theory behind the magic. So there are all good reasons to know at least what kernels are and how they work and how they're important. So now, okay, I'm comfortable with it. Okay. Minimum norm linear regression. We're walking towards more modern things now. So let's consider the case where we have n less than p, so the case where we have fewer data than the dimension of the vector that we're trying to estimate, but that x is full rank, so there are no repeated points, essentially. I have no repeated points in my training set. Of course, as I said before, as we saw before, if I try to solve the least squares problem, it doesn't have a solution, because it's like a situation where you have fewer equations than unknown. So you can think of the number of observations as the equations and the unknowns as the dimension of W. Okay, you have this situation where n is less than p, number of equations is less. And so there's infinitely many solutions to this least squares problem, because there are many choices of W that lead to that being exactly 0. Okay, and so you know that least square solution belongs to the argmin. It's one minimizer of that, but there are many. There is not just one. There are infinitely many. There's a continuum, actually, of solutions. And minimum, so that's what I just said. And minimum norm linear regression says among all the solutions, so among all the W's that satisfy that y equals xw, which is the same as saying that the norm of y minus xw is 0. Just among all those that satisfy this, that minimize the least square solution, let's try to find the one that has the minimum norm. And this is called the minimum norm linear regression. And it has a closed form solution, which you can see immediately. It's the thing we just saw in the dual variables, when you invert x transpose rather than x transpose x. But so it's the limit when lambda equals 0. So in the previous slide, we were looking at x transpose plus lambda I minus 1 xt. It's just this, but without the lambda, with lambda 0. Okay, so minimum norm solution is just this case. So for those of you who had an advanced or reasonably advanced linear algebra course sometime in the past, you'll probably recognize that this is one instance of something called the Moore-Penrose pseudo-inverse. Okay, who knows about Moore-Penrose pseudo-inverse? Anyone? No one? Wow, your linear algebra courses are bad. So Moore-Penrose pseudo-inverse is, it's essentially the following idea. So actually these Penrose, anyone heard about Penrose? Yeah. Okay, the Emperor's New Mind. So this guy who proposed this quantum theory for consciousness, and he's also a Nobel Prize winner. You won the Nobel Prize in Physics in 2018, 17. because of black hole physics and cosmology. He's a very famous physicist, but this is a mathematical property, mathematical object. So if you have a linear system of equations, standard, as many equations as unknown, you have a system matrix, you solve the system by inverting the matrix. That's it, okay? What if you have more equations than unknowns? Okay, that you can, there may not be a solution. You have more restrictions than unknowns. In that case, you solve the least square solution. You find what is the solution that least violates this equality. And you go from, so you're trying to solve a problem which is ax equals b. So this is a detour, but it's good to know. I think it's this kind of math thing that everybody should know. You have a system like this. If matrix A is square and invertible, you just do A minus 1b and you have x. That's it. Okay. Now, if A has more lines, more rows than columns, you have more equations than unknowns. So it's an overdetermined system. There may be no solution. Okay. And then instead of trying to solve this, you give up and you try to solve these. What is the solution? Sorry. You try to find what is the x that least, well, sorry. You try to minimize this. What is the x that minimize the sum of the squares of the violations of these equations? And this is just a least square solution that we saw. So the solution to this is exactly linear regression. It's x equals A transpose A minus 1 A transpose B. So this is the Moore-Penrose inverse. This is called the Moore-Penrose inverse for an equation, for a system of equations, or for a matrix that has more rows than columns. The other case, which is, suppose now that A has fewer rows than columns. So you have more unknowns than equations. So the problem is underdetermined. There are many solutions, okay? So you can find many solutions, but you need to choose one, okay? And the one that you choose is the one with the minimum norm. You solve this problem down here, that's there on the second line. You solve this problem. Among all the solutions, choose the one with the minimum norm, and you get A transpose minus 1 AT x B. Okay, and that's the other Moore-Penrose inverse. So, and if A is invertible, the Moore-Penrose inverse is just the inverse. Okay, so the Moore-Penrose inverse is a family of ways of solving linear systems that gives you the standard way, which is just invert the matrix if it's square and invertible. It gives you minimum norm solutions if you have fewer equations than unknowns, and it gives you the least square solutions if you have more equations than unknowns. Okay, this is the class of Moore-Penrose inverses. If you're interested in knowing more, there's a very nice Wikipedia page about Moore-Penrose pseudo-inverses. Okay, and they have lots of nice properties. So we have perfect interpolation regime. This is called the perfect interpolation regime because we can find a solution that has a small norm and that perfectly predicts the points. So it's a function that goes exactly through all the points. Okay, so if you're fitting a polynomial with the order exactly equal to the number of points, for example, or an order that's higher than the number of points. If you have 20 points and you try to fit a polynomial of order 40, you have a solution that goes exactly through all the points. Okay, and then it's crazy between the points, but it goes through all the points. It's perfect, does so-called perfect interpolation. Why is this important for modern machine learning? Because this is the lens through which we should view modern machine learning. Okay, modern machine learning. Have anyone seen this? Double descent? Yeah, good. So double descent, now I'd like to go back to these very basic linear algebra things because this is exactly how this is set up. So reconciling modern machine learning practice and the classical Bias-variance trade-off is a very famous paper now by Misha Belkin and two other people and three other people. It's published 2019, I think, yeah, 2019, so not that long ago, 6 years ago. And the idea was, how can we understand modern neural networks, which are so big, they have so many parameters. Typically, sometimes they have more parameters than the size of the training set from which they're being trained. How come that they work? We are completely off the charts for what was the standard view of machine learning that we already saw before. We saw it when we looked at the Bias-variance trade-off. We have this complexity of the representation. And then if we have an overly complicated model, it starts to, the test error starts to go up again, and there's an optimal solution somewhere. There's an optimal complexity there. And what happens is that if you go over the capacity, if the capacity goes over the interpolation threshold, what is interpolation threshold? Is a complexity above which you can fit the data perfectly. Think of polynomial regression is a simple thing to keep in mind to understand this. You have 20 points. In the interpolating regime is fitting a 20 order 20 polynomial. If you fit any polynomial of order above the number of points, you can do perfect interpolation. You can make the polynomial go exactly through the points. Okay? But if you keep on going, the surprising thing happened. It seems like it's a bad idea to use a polynomial of order 40 to fit 20 points. Doesn't make sense, right? But it does. If instead of just doing least squares, which you cannot, so notice that when you move beyond the interpolation threshold, you cannot do least squares solutions because they don't exist. What exists is the minimum norm solution. And if you switch from the least square solution to the minimum norm solution and keep on going in the complexity, the error starts going down, and on the right side you have errors which are lower than the best thing that you can obtain on the left side. Okay, this is called the double descent phenomenon. It generated like a flow, like that. There's this avalanche of papers trying to explain these in different models. So it's a very active research topic still today. And these are some actual examples. This is just a picture, but these are actually examples. Okay, this is for something very famous, which are the random Fourier features. So random Fourier features. So you need to get away from the issue of learning the features. So the features are just, in this case, are just either fixed or random. So I don't know, maybe you've seen. So I mentioned a while ago Ben Recht, this guy Benjamin Recht, who's a guy from Berkeley, who said that calling least squares AI is a bit of a stretch. He got a test of time award at NeurIPS maybe 4 years ago or something for a paper that's like from 10 years ago, which is called, I don't know, everything and the kitchen sink or something, the kitchen sink, something, it had kitchen sink in the title, I don't remember, which is about random Fourier features. So random Fourier features are very simple. If you don't know what Fourier means, that doesn't really matter. It's just a way of computing features. I have a vector X, and you compute a set of features which are computed like that. You sample random vectors VI, you compute these random vectors in a product with X, and then you compute the exponential times square root of -1, and these are your features. These are complex numbers, but it doesn't really matter. Okay, it's just a bunch of features. Now we're going to try to solve fitting some problem. It's a very small data set with only 10 points, as you can see there. It's 10 points, and you look at the test performance. This is for a 0-1 loss. They formulated a classification problem. It doesn't really matter. We can only look at only at the left or the right side, which is what we've been looking at, squared loss for regression. And on the left side of that peak, we have the standard Bias-variance trade-off. The mean squared error goes down and then goes up again. Okay, and then it actually explodes to very large numbers when you have as many features as points. Okay, but then if you keep on going and if you keep adding more and more and more features, actually the test error starts going down. And it goes down to values that are lower than the minimum that you can get on the left side. Okay, this is the double descent phenomenon. Now, if you look at it's very important to keep in mind that we are not solving the same problem. On this side, we are solving least squares. On this side, we are solving minimum norm. They are two different problems. Okay, so all the points on the right side, as you see now in this plot here, we see it's training error. Here you see that beyond 10, training error is 0 because we're fitting the data perfectly. I have enough features to have 0 error in the training set. It's called overfitting typically, but it's benign overfitting because there's no problem because the test error is going down. It keeps on going down and it goes down to low values. And in the middle plot, what you have is the norm of W, and we see that because when we're doing least squares, we have no control on the norm of the estimate of W. It is what it is. Okay, we're not controlling it. We're just trying to minimize the error. The norm goes and the norm explodes because when you approach the interpolation limit, the function is making a big effort to try to minimize the least squares, and it gets really big coefficients. And in the peak, it has really large coefficients, really large norm. It's 400 and something. But then interpolating regime kicks in, and you change the criterion to minimum norm, and you try to control the norm, and the norm starts coming down. And the norm can come down because as you have more and more features, there's more degrees of freedom to adjust the functions so that you can still interpolate, but still minimize the norm. And the norm comes down and goes down to a lower value. I'll try to show another example of this. So this is another picture for a different example. Same plot, but this I'm going to try to show it. This is a real case. This is a very dramatic case. So the function is over there. I don't know if you see it. So this is the true underlying function. It's a really nasty function. 2x plus cosine of 25x. Okay? Really bad function. And you're going to do, this is going to be Legendre polynomials, but that's completely irrelevant. It could be something else. Okay? It's some collection of polynomials. And this is the plot we have here is training error and test error. The test error is the blue line. And we see the double descent. So we see that on the overparameterized regime, the lowest possible mean squared error, error is lower than the minimum possible on these underparameterized side. And the orange line is the training that with this is logarithm scale. So the training error is going to, the log is going to minus infinity because the training error goes to 0, okay, as you cross the interpolating regime. So can we try to kind of visualize what's happening? So here it is. So on the right side, you have the blue is the true function, and you have 20 points, 15 points. So imagine fitting that function, the blue function, with only those black points, okay? Not so easy, right? So if you use an underparameterized model, so you try to think of these as just standard polynomials. You try to fit a not very high order polynomial, you get that kind of thing. Not too bad, not too good, sort of not. Now, if you in the hope of trying to get those oscillations, you start increasing the order of the polynomial. As you approach an order of polynomial which is close to the number of points, you start getting these things which they almost go exactly through the points, and then they become really crazy in the middle of the point, which is very well known, right? When you are exactly at the same order as the number of points, you get these, and this is terrible. The prediction error of this function is horrible because away from the points, it's just doing crazy stuff, okay? And then if you go a little bit above, it starts getting a little better, but not too much. But if you go really above the interpolating threshold, you end up with something like this. Because the minimum norm criterion starts kicking in. It has many more weights to fiddle with. And you can actually do a good job at interpolating the points, as it does, without getting too crazy in the middle. Notice that this is a very, very high order polynomial. Look at this wiggling here. But in terms of prediction error, it's much better than the one with the lower underparameterization. Okay. So this is a nice example in this paper, which is cited over there, Schaefer et al. 2023. I can put the reference in there in detail. Okay. So we've talked about something which is from the last 5 years, not 50 years old. Okay. Another thing which is very important that it's very easy to do in the linear regression case is uncertainty estimation. Okay. So it's very discussed nowadays that machine learning methods should be able to guess their uncertainty and to provide measures of uncertainty. And I need to speed up a little bit. So, but I just want to show you that in the linear regression case, everything can be done in closed form. You can do everything in closed form. So we've seen these that when we're doing least squares regression, we are assuming that there is a Gaussian noise model behind. When we're doing ridge regression, you're assuming that we have a Gaussian prior. And then in this case, everything is easy to do in closed form. If you ever did a class on probability estimation or Bayesian estimation, you know how to do this. This is all very simple. Multiply a Gaussian by another Gaussian, and you get another Gaussian. And we see that we can actually, more than just have the ridge regression estimate, which we know that. I'm replacing X by D now. This is what we used to call X. Doesn't matter, but because I'm using X for something else now. that's the ridge regression estimate, X transpose X, blah, 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 blah. We also know the covariance of the estimate. We know how the estimate fluctuates around the mean, okay? And it has a closed form. It depends only on the design matrix and on the parameters of the model. And so when I want to predict at a new point, now I know that when I have a new point, say X star, I know what the prediction is going to look like. It's going to be X star multiplied by a Gaussian variable that has this distribution plus some noise, which is also Gaussian. And so all of these can be done in closed form. It's very easy. It's just multiply a vector by a Gaussian and add another Gaussian. Everything is just linear Gaussian. It's the ideal situation. I have no time, of course, to go into the details. I don't want to go into the details. Just call your attention to the following fact. This is, on this side, it's the uncertainty of your prediction. And the uncertainty depends on where you are. It depends on X star. Okay? So let me skip the next slide and then I'll come back. Okay? So if you're doing this, say, fitting a polynomial, a quadratic polynomial to those 5 points, very simple problem. It's a very low dimensional problem. You fit a polynomial, you get that nice blue line. And the vertical bars are the noise bars. Those are the noise bars from the noise that you know was in the data. But that's not very useful because it tells you that the uncertainty is the same everywhere, which is not. Okay? If you actually do the Bayesian regression computation in the previous slide, and you take into account that the variance depends on where you are, you actually get these error bars, which depend on where you are, and it makes a lot of sense. It says near the data, the uncertainty is not too big. As you move away from the data, the uncertainty increases. And that's contained in these expressions for the variance of the prediction. What do you mean by this variance? If you produce different samples from the posterior on W, from the distribution of W given the data, and you look at what the functions look like, if you plot several samples, they look like this, which means that near the points, they don't fluctuate too much. They cannot because they need to be close to the points, but far away from the points, they fluctuate too much. So this uncertainty here that we see here is essentially what is being shown here, this uncertainty here. So this point in this red line here is the average of these lines, and this fluctuation is that standard deviation over there. So I don't want to go, we have no time to this, but just so in the linear, one very interesting fact about linear regression is that we can do the full Bayesian thing, including estimating the uncertainty in closed form using analytical tools without any need for sampling or anything. It's the only case, fortunately. It's a very hot topic in machine learning, in deep learning. There's a whole, if you go to a big machine learning conference, there's lots of papers about Bayesian deep learning, how to produce estimates of uncertainty estimates at the output, and it's computationally difficult. You need to have some tools. Another thing that's very reasonably recent topic in machine learning is epistemic and aleatoric uncertainty. Anyone heard about these two terms? Yeah, a few people. Okay, so epistemic and aleatoric uncertainty. So so epistemic, it's like the root word for epistemology. It's the science that studies knowledge. It's about what we know about the model. So epistemic uncertainty is the uncertainty that I have in my predictions that originate in the uncertainty in estimating the parameters of the model. It's contained in the estimation procedure. And the aleatoric uncertainty is an unavoidable type of uncertainty that comes from the fact that the data is random and there is randomness in the data. Okay, and it's sometimes very important to separate the two, to see when I have uncertainty, what fraction of the uncertainty comes from my uncertainty about the model, what fact comes from the fact that there is noise in the data. Okay, and it's quite, in the linear regression case, it's very easy to write down. In the other cases, it's very hard. So that's another reason why it's good to start with linear models. So there's a not very famous, but pretty well-known law in probability theory called the law of total variance that says the variance of a random variable can be decomposed in the following way. You have another variable, v, okay, and this can be written as the expected value with respect to v of the variance in u given v, plus the variance with respect to v of the expected value of u given v. It's not very easy to swallow. If you've never seen it, it takes 5 minutes to read and to understand what's going on. I don't expect you to, if you have never seen it before, I don't expect you to grasp it right away. But if we apply it to this problem that we were trying to see before, which is U is my prediction. So U is my prediction for the response at some new point x prime. I want to know what is I did some regression. I got an estimate of the coefficient parameters. I know the covariance. And now I want to predict at a new point, x prime, and U is going to be that prediction, okay? And V, in the above expression, is going to be my prediction, my estimate of the parameters of the model, okay? If I apply this law of total variance above, we see that the variance in the prediction can be written as a term which corresponds to the first term above, which is the aleatoric uncertainty. Aleatoric uncertainty is the variance of the predict for a given W. What is the variance of the prediction? And then you average these for all possible W's. And that gives you what's called the aleatoric uncertainty, because it's the uncertainty in the fact that even if W is fixed, Y is random because it has noise, okay? And the other one is the variance. It's the variance with respect to W, so it has to do with the fluctuations in W, in the estimate of the parameters. And for each W, you know what is the expected value of the response, but now this thing fluctuates because W fluctuates. And you need to compute this, how much this fluctuation is, okay? And these two components are called the aleatoric and epistemic uncertainty, okay? I know this slide takes, if you want to understand this, you need to read this and you need to read the literature on this. I just want to warn you that these things exist and they're very important these days. So aleatoric uncertainty is the expectation of the variability for each W, and the epistemic uncertainty results from the variability in the estimates of W themselves, okay? And in the linear regression case, it's very easy to identify them because the posterior in Y, so we had it in the previous slide, this long expression here, blah, 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 blah. I can write it very, very compactly in this way. It's just this. It's just some inner product of some new point with some parameter vector and plus the thing that I care about now because I'm estimating uncertainty, which is the covariance. And so there's an epistemic invariance, which is X transpose CX, where C is this big covariance matrix, it doesn't matter. The important thing is that it depends on where you are, okay? So in this plot, the fluctuation in the width, the fluctuation in the size of the bars is due to the epistemic uncertainty, not the aleatoric uncertainty. The aleatoric uncertainty is fixed. It's just the noise variance, which is always the same everywhere, okay? This change in height comes from the fact that your uncertainty about W is more serious when you're far away from the observed points than when you're close to the observed points, okay? And so, blah, blah, blah. In this case, the aleatoric uncertainty, as we saw, is just the noise variance, sigma 2, and the epistemic uncertainty is that quadratic thing that depends on where you are in space, okay? So it's a very important topic for modern machine learning. There's lots of people working on how to do this when the model is more complicated, how to do this for a neural network. You have to do stuff like Monte Carlo dropouts and complicated stuff. But it's important to understand how it works in a simple model where you can do everything in closed form. That's where you get the insight of what's going on. So just very, very, very briefly, there's another way of say, regularizing which is alternative to REACH, which is to instead of L2 norm squared, you can put an L1 norm. So L1 norm is just a sum of the absolute values of the weights. This is sometimes called LASU, least absolute shrinkage and selection operator, or L1 regularization. If you train any model using PyTorch or whatever, there's an option to use L1 regularization in the model. I'm not going to go into the details of these because we have no time. As usual, I go too slow. One important observation is that differently from what happens when you're doing weight decay or ridge regression is that when you use L1 regularization, some of the coefficients that you estimate are going to be exactly zero, not approximately zero, exactly zero. Okay, so using L1 regularization encourages some of the coefficients to become exactly zero. I have no time, no chance to explain why. The thing is that it's much harder to solve computationally because the one norm, which is the sum of absolute values, is not differentiable because its absolute value function is not differentiable at the origin. You cannot compute derivatives at the origin. Although in modern machine learning applications, you just ignore the fact and do gradient descent, and it works. That's it. Using gradient descent, simply pretend that L1 is differentiable and carefully adapt the step size. That's what is typically done. So, classification. Now let's jump to classification, and I have already seen that I need to skip I need to move yeah, we'll see. So in a nutshell, classification is, it's the same picture as in regression. Let's produce a machine that predicts or estimates or guesses now a class, not a quantity, but a class from variables or features at the input. So it's the same picture, okay? It's maybe the core machine learning problem, maybe arguably regression or classification. But if you think machine learning, the first thing that comes to mind is probably classification. And again, the task is the same. You want to learn this machine, find the best possible machine from a set of training points. Okay, so the way I like to start it, there are many ways to start it, but to do the most classical versions of this is, let's assume that this is sort of equivalent to what we saw in the slide where in linear regression, we assume that we have some clean data to which we add Gaussian noise. Here, the equivalent to that is we have some scores. So each of these, I have some point X, and each of these quantities, I'm going to call it a score for class Y. Okay, so I have a collection of vectors, eta 1 to eta k. So I have k classes. I have a collection of vectors, eta 1 to eta k. Okay, so each class will be characterized by a vector of parameters. And for each point that I want to classify, I compute the score for all the classes, compute the exponential of the score, divide by the sum of the exponentials, and I get quantities that are necessarily larger or equal than 0 because exponentials are larger or equal than 0. And by normalizing, I get a collection of quantities that are larger or equal than 0 that sum to 1, so I can interpret them as probabilities. So I know that I get a collection of numbers that satisfy, if I sum y from 1 to k, I know that f of y given x is 1. So I can see this as the probability of class y given x. And this is an assumption. I'm going to assume that my data is generated like this. There are underlying parameters that I don't know, and every time I get an object, the object assigns itself a class by sampling from this distribution. Okay, it's sort of an assumption. So this is the training data. So each yi is a sample from this distribution, and the samples are conditional independent. Okay, maybe many of you probably have recognized these as being called, what is it called? Softmax. Good. Well, okay. So because all the data is independent, the log likelihood of the training data, again with the conditional independent, just the sum of the log likelihoods. Okay, and a nice way to write these is just to sum across all the points, and now sum also across the labels, possible labels, 1 to k, but multiply for each point, I multiply by this indicator. So 1, this quantity here is 1 if y equals yi, and it's 0 otherwise. Okay, it's sort of a one-hot representation of my class. And this is modernly called, as you probably many of you know, as the cross-entropy loss. Okay, so underlying the cross-entropy loss, there's this assumption that my data is generated randomly according to this softmax model. Okay, so in the binary classification case, it's particularly simple. Let's look more in detail into the binary case. In the binary case, you have only two classes. I have only two parameters, eta 1 and eta 0. And so, for example, the probability for class 1 conditioned on the input is just like that. And for the class 0, it would be with 0 up there. And just by multiplying, dividing both numerator and denominator by the exponential of eta 0, I can simplify the expression to this expression down here, where W is just the difference between the two etas. Okay, so when you're solving a binary problem, you only need one parameter vector, because if you know the probability of one of the classes, the probability of the other class is 1 minus the other. So you only need one vector of parameters, not two. for the binary case. In fact, for k classes, you don't need k parameters. You need k minus 1 because you always get the last one, but you don't typically use that. Okay. So the shape of this function that looked like that was here, sorry, exponential of something divided by 1 plus exponential of something, which is called sigmoid. I'm sure most of you have seen it before. It looks like this, exponential divided by 1 plus exponential. Obviously, the probability for the other class is 1 minus this one, so it's like it's symmetric of this function, something that goes like this and goes like this. So this is the probability of the other class. So if we're looking into dimensions, it looks like this. It's just some sigmoidal function in some direction in space. And we can think of the place where it crosses 1/2 as being a sort of a boundary, a decision boundary. So you choose the blue class if you're above the boundary, you choose the red class if you're below the boundary. You all know this. So what about solving the maximum likelihood problem? So there's a classical way of writing these, which will lead to the equivalent to softmax, is the probability of some class, if classes are 0, 1, is the probability of class 1 raised to the label, probability of class 0 raised to 1 minus the label. So if y is 1, you get the first thing because you're raising it to 1, and you're raising the other one to 0, and anything raised to 0 is 1, sorry, and vice versa. So this is, once you do the manipulation and simplify, you get this thing that you need to solve, which is called the logistic log likelihood. I'm going fast, I know, but I just wanted to know this stuff exists. So the maximum likelihood estimate, which is sort of what we had for the least squares estimation in the regression case, now it's you need to minimize this function. But as you can see, this function is much more complicated than just sum of squares. It's much more complicated. It involves logs. It has this very nasty thing, which is a log of a sum. Logs of products are great because they become sums of logs, but logs of sums are nasty because a log of sum is something that you cannot get rid of. It's in there. And so it's very hard it's much harder to handle. And so it has no closed form, and we certainly need optimization algorithms to solve this problem. Okay? It's not too bad in the sense that it's smooth and convex, should not be too hard, and it's not too hard. Okay? You can add the reach term, you can add regularization, you can add this extra penalty to try to avoid W from becoming too large. So one thing that or you can add reach. One thing that is important to know is that this problem, if you have a data set that is perfectly separable, if you have a data set where all the points in one class are here, the points in the other class are here, and there is a perfect linear separation between them, this problem has no solution. It seems like it's the easiest case, but in terms of computation, it's actually nasty because the function is unbounded. You can get you can keep on growing and growing and growing, and it never stops because it's kind of converging to a sharp boundary, which in this model corresponds to having W with extremely large values going to infinity. Okay, so it's hard to handle separable data, although it seems to be the easiest case. It's actually easy because you can solve it just by adding this term, like you do in regression. The problem is solved, or L1. It doesn't really matter. So you can use L2, L1, or as in deep learning. Okay, in the multi-class case, we already saw this. We saw it's the generalized linear model, and if you want to write the log likelihood function, we've seen this before. It's just this. It's just the cross entropy loss. It's just the sum across all the points, sum across all the labels of these one hot representation, which is actually explicitly mentioned in the next slide. So the L of W, so the multinomial logistic loss or cross entropy loss, as is known nowadays, it's just that. Okay, you just notice that what you're doing is essentially trying for each sample, this guy, what it does, it selects the correct class and tries to choose W such that the probability of the correct class is high. It's trying to adjust W such that the predicted probability of the correct class is as high as possible for every point. Okay, so this is what's inside this. Actually, I wrote a comment on that. Notice that if Xi is in class K, minimizing L of W pushes this score up, It's trying to push this score up, which is the score that corresponds to attributing a high probability to that correct class. Okay. So I'm going to skip these. We can also do Bayesian logistic regression and actually estimate the uncertainty around the boundary. But you have to read the slides because we have no time to go and reach in detail. Okay. It's not in closed form. You cannot do closed form even in this linear classification model with logistic regression, which is arguably the simplest approach to classification. You cannot do the Bayesian version to estimate uncertainty around the boundaries in closed form. You need to use either approximations or some sampling methods. Okay, but it can be done. It's not too hard. It can be done. That's an example. This is in Kevin Murphy's book, which I'll mention in the end. So another view, which I think is worth knowing, now this is much more modern, is to look at classification in this way. Okay, so we have, when we're doing classification, we have two things, two parts. So there's an input, there's some linear or nonlinear stuff in there, could be a very deep network, doesn't matter, something, and in the last layer, you have some scores, okay? And then you need to transform those scores. If your goal is not just to estimate which is the highest score and be done, if you actually want the probabilities of the classes, you need to transform those so-called scores into probabilities, okay? And we already know that, we saw this before, that we can do this by using softmax, right? You can just compute the exponential of each z and divide by the sum of the exponentials. That would be a softmax layer. But let's see this in a more general sense. So we have the scores. It's a vector in Rk, no constraint or it's just an arbitrary vector in Rk. And you want to compute probabilities. You want to compute probabilities of each class, which is probability that your point x is in class k, which means that y needs to belong to something called the simplex. Everybody knows about the simplex. No one ever, who doesn't? You do? You do? The only one? No one heard about the simplex? I can't believe it. Oh, a lot of people. What? No. That's another, that's for linear programming. No. Simplex is a set. This is a very fancy name for a very simple object. The simplex is just a set of probability distributions. So the simplex is just a set of vectors in some dimension where all the components are larger or equal than 0 and sum to 1. It's just a probability distribution. It's just a compact way of writing a vector belongs to the simplex if it corresponds to probability distribution. And it's simplex k minus 1, you may wonder, but this is a detail, but why do I write k minus 1, not k? Because it's a k-dimensional object. Why? It sums to 1 because I don't have k degrees of freedom. I only have k minus 1 degrees of freedom because you need to sum to 1. One of them is 1 minus the sum of the others. So mathematically, are there any mathematicians in the room? Anyone from math background that's really mathematician? Okay, good. So from a mathematical point of view, the simplex is a k minus 1 dimensional manifold. It's not a k dimensional manifold. Okay, so I want this map to satisfy certain properties. The most important one of them is that the order of the scores is reflected in the order of the probability. So if two scores are the same, I need the probabilities to be the same. No reason to favor one or another. And if one score is bigger than the other, I want the probabilities to satisfy the same property, maybe with equality. Okay, because maybe there is some time. Okay, so I want the probabilities to somehow reflect the preference for the classes that's embedded in the scores. And so there's many possibilities. Okay, one of them is let's look for the probability vector that is most aligned with the scores, that aligns better with the scores. And how do you find the vector that's most aligned with another vector? You maximize the inner product, but it cannot be just any vector. It has to be a vector of probabilities, it has to be in the simplex. And the solution to this very simple problem is just find the maximum. So there's this person that knew about the simplex method, so probably seen linear problems. This is a well-known property of linear problems. They have this very simple solution. If you don't believe this is so, just think of the following. Think you have an amount, 1 million euros that you're going to invest, okay? And you have different banks that are giving you different return rates. These would be the scores, Z. How would you distribute your money through the banks? just put all the money in the bank that gives you the highest rate, right? There's no reason to, assuming there's no risk, nothing like that. So if you want to maximize, if you want to assign, to distribute a certain amount of mass, in this case 1, through different scores, of course, the best way is to choose the maximum one, that's all, okay? That's the solution, argmax. So one way of projecting vector of scores into a probability simplex is just look at what the maximum score is and output a probability distribution that's 1 at that coordinate and 0 everywhere else. Simple. But this may be too bold. You'd say, oh no, I'm risking too much. I want to be a bit careful. And so I want to somehow favor that this distribution is not so peaked. And one way to do that, and if you don't know about Shannon entropy, who knows about Shannon entropy? Yeah, good. So one way of doing this is, okay, let's try to find this P that maximizes the inner product, but let's add the entropy. So Shannon entropy is the sum of the PI's log PI's with a minus, and it has this property, which is it's maximized when all the probabilities are the same. Okay, so all the probabilities are the same, 1 over k, then it has the maximum value, which is log k. If one of the probabilities is 1 and all the others are 0, this has the minimum value, which is 0. Okay, so by adding these to the objective function, I'm balancing two objectives, which is on one hand, I want to be aligned with z. On the other hand, I want the distribution to be slightly not too far from uniform. Okay, and I can actually add some coefficient to balance the weight, but I will not do it. and if you, so the entropy satisfies this. I just said it's always non-negative, and the maximum is attained when all the distributions are the same. And if you solve this problem, which can be done, it's very easy. I'm not going to do it. It's a standard optimization problem. You get softmax. Okay, so softmax can be seen as a solution to this task of trying to align your probabilities with the scores, but producing probabilities that are not too unequal from each other. So you try to be a bit more careful in what you predict. And you can actually change these by multiplying these by some, well, I'll say it in a second. I have it in a slide. Okay. So this is encouraging high entropy. This is what I was going to say. You can actually multiply one of the terms by beta. In this case, you can give more weight to aligning with Z or less weight to aligning with Z. And the solution, so this is how to solve the problem. You get these softmax, but with the beta coefficient up there. Instead of just exponential of the scores, you get exponential of beta times the scores. And the inverse of beta is nowadays, and always has been, known as the temperature. So 1 over beta is the temperature, or 1 over the temperature is beta, is the same. Okay, which is very talked about when you talk about language models. What should be the temperature at the output layer? Higher temperature, more randomness. Lower temperature, less randomness. This is what the temperature is. Okay, and so if you solve the problem, you get that softmax beta z. So if beta is high, you get a more sharp distribution. If beta is low, meaning that you have a high temperature, you have a more uniform distribution. Okay, another alternative, which is actually invented by 2 people in this workshop. Then Ramon is somewhere over there. He was around. Is he there? Outside. And André Martins, one of the founders and organizers, they wrote this nice paper in 2016 called Sparse Max, where they have this kind of seemingly naive observation. Why not just project? Why not just take the score and project on the simplex, just Euclidean projection? Okay, find the vector in the simplex that is as close as possible to my score vector, but in the simplex. Okay, and the solution to this is called sparse max, by contrast to softmax. Anyone here heard about sparse max before? A few, yeah, good. Andrea will be happy, and Ramon. And it's interesting to notice that we can, if you expand that square of difference there, you can write it in this way there. Plus would be the norm squared of z, but norm squared of z is irrelevant because you're maximizing with respect to p. And so you get that form there. And actually this quantity there on the right, p squared, norm of p squared, note that that's just the Euclidean norm of a probability distribution. You just take the probabilities and square them and sum, which looks like something strange to do, but it's okay. It's actually called Utsalis entropy. It was proposed by many decades ago by a guy called Konstantin Utsalis. And so this is kind of an entropy idea. And so there's this whole family
where omega is some entropy, not necessarily Shannon, could be Sally's entropy. And there's so Ben, who's also around, not here now, he's one of the monitors, has a paper where he proposes this alpha and max, which is a generalization of these to different types of entropies. Okay, so this is nice to know. So all of these, argmax, softmax, sparse-max, all of these ways of mapping from scores to probabilities satisfy these several important properties. So for example, if you add a constant to all the scores, so if you take all the scores and add alpha to all of them, nothing changes. The probabilities don't change. Okay, it's obvious, like in the softmax, you're just adding a constant to all the exponentials, the same constant, which is the same as multiplying all the exponentials by the exponential of that constant, and then it cancels out when you divide by the sum. In argmax, of course, it doesn't change because it's just choosing the maximum of a collection of numbers. If you add the same constant to all of them, the max is in the same position. In sparse max, there's another reason why it doesn't change, because you're computing a Euclidean projection on the simplex. And when you add a constant to a vector, you're actually moving it perpendicularly to the simplex because you're adding the same number to all the points. The projection doesn't change. You're moving in a direction perpendicular to the simplex, and the projection doesn't change. Okay, so there's rich reasons why all of this is satisfied. Okay, permutation invariant, of course, is very important. If you permute the scores, you get the same permutation in the probabilities, which has to be. And this is how it looks like. So, for example, in the two-class case, the sigmoid, which looked like this, the softmax, which is the sigmoid, is the blue line. The sparse max is piecewise constant. It gives probability exactly 0 or exactly 1 when the score is above or below a certain threshold. On the right side is for the two-dimensional case, or this is another example. We have the scores that look like this. So if scores look like that above, 1.07, blah, blah, all those numbers. And if you do softmax, you get a collection of numbers that are non-negative and sum to 1, but they're all non-zero. If you do argmax on the right, you just choose the maximum number, which is the first one, 1.07. All the others are smaller. Okay. And if you do sparse max, it's something in between. It's not just one, it's not all, it's a few. In this case, it's the two biggest ones. But this is not the same. People always get asked the question, what about, why don't you just add the fact that you just need the 2 or 3 bigger ones? Because this is not what this is doing. The number that it provides, the number of non-zeros depends on the scores. It's adaptive. It depends on how uneven the scores are. Okay, so now that is what I was talking about, the temperature. So the beta is the inverse of the temperature. So in both cases, we have that before computing the softmax or the sparse max, we take the scores and divide by this temperature, which is the same as multiplying by beta, which what we had beta before. We have these two important limits, which is the limit as temperature goes to 0. Both of softmax and sparse max will be just argmax. So this is like in thermodynamics, if you studied physics, the zero temperature limit of the system is when all the molecules are in the lowest possible energy, so which is the highest probability state, or in the high temperature limit, all the states are equiprobable. So when you take the temperature to infinity, both the softmax and the sparse max converge to a uniform distribution. So somewhere in the middle, there are intermediate cases where not everything is the same, but it's not just a maximum. You have several probabilities. So the temperature controls how peaked softmax is and how sparse max is. Yeah, sure. Sorry? Good question. Well, if you in situations where you have, there's lots of situations where you should use sparse max. If you want say, in a very simple case, say just classification, okay? If you just want to know what are the most probable classes and you want the probabilities for those, not for all of them, you have 1,000 classes, and you guess that you just want to know what the probability, it will be enough to know what the probabilities of the most probable classes is, then you should use sparse max because it kind of only gives you the probabilities of the most probable classes. Okay, without you saying a priori, I just want the 10 most probable classes. That would be very easy, but sparse max will give you enough classes, not all, but enough classes to contain certain amount of probability. That's what it seems to be good enough. And it will be adaptive. It will depend on how uneven. If the score is extremely uneven, it can even be equivalent to argmax and give you just one, if it's very uneven. If it's not so uneven, it will give you a few. If it's really quite kind of even, it will give you many. Okay, it will adapt the sparsity. So actually, one of the main motivations for which they created sparse max originally was for transformers, which we'll not talk about today, because in the softmax, I'm sure some of you have seen transformers and you know the softmax in the transformer. And if you replace softmax by sparse max in a transformer, you get a linear combination of the values, which is a sparse combination. It only uses some of the values, not all of them. So softmax with low temperature is like a differentiable version of argmax. I haven't covered here, but argmax comes with its own loss function, just as the cross entropy loss corresponds to the softmax transformation. There is a loss which is called the sparse max loss that corresponds to the sparse max transformation. So this is differentiable, and there is a toolbox that has sparse max and the sparse max loss, which is fully differentiable. You can plug it in PyTorch and use it as if it was softmax. But I usually had a slide with that, but I removed it because it's just too much. Any other questions? Okay, so I'm just about to finish. I'm not going to go all the way to the end because we're about to get out of time. So I just want to go over this very quickly. So the loss function perspective. So if we have a binary classifier in the simplest version, if I'm not doing softmax or anything, it's only for two cases. One very simple thing that I could do with my score is just compare it with the threshold. Okay. If it's above 0, I say class 1. If it's below 0, I say class 0. So this would be a hard threshold classifier. And in the linear case, this function that produces the score is just the inner product of the input times some parameter that I'm trying to learn. Okay? And so I can summarize the loss for both logistic regression and support vector machines and sparse max and all of these can be seen as being formulated like this. I have some regularizers, say norm 2 of the weights. In this case, I've moved the weight from W to theta now. And then there's a loss, and I'm computing the average of the loss across all my data points. And notice that the loss depends, of course, on the score function and on the label for that particular point. Okay, so we can write the logistic loss in a compact version like this. We can write the hinge loss, which we didn't talk about, like this. But the important thing is that I just want to look at the picture. What really basically doing is, so on the bottom, on the horizontal axis, I have the label and the score. And I want the score to have the same sign as the label. If the label is positive, I want the score to be positive. If the label is negative, it's bad. So I want to penalize, whenever the label is on this side, I want to penalize the score. If the score is high, I want to penalize it. And if I would just count, if my loss was just counting how many wrong classifications I have, I would just attribute loss 0 if I'm right, loss 1 if I'm wrong. And this would be this step function over there. But the problem with the step function is that it's not convex, not differentiable. So just finding theta that minimizes the number of errors, which would be just this, what the loss would give you. We just count how many errors I have for that particular theta. It's solving a linear classifier to minimize the total number of errors is an NP-hard problem, if you know what it is. So it's a hard problem. So what all methods in machine learning do is, okay, I cannot do that, but I can approximate this function, this step function, by some convex function that's continuous, and if it's convex and continuous, I can do optimization. Okay, so you can summarize machine learning in the classification case by what is the best convex and continuous approximation to the 0-1 loss. Okay, and there are many. Exponential binomial deviance is logistic, squared error, support vector machines. Sparse max is not there, but there's one for sparse max. And so this quantity that we minimize, which is the average across the training set of the loss, can be seen as this is where we started, as a sample-based version. It's an estimate based on data of what I would really like to have, which is what is the expected value of the loss if I could know the joint distribution of X and Y, but I don't. I cannot compute the expected risk. This is always the goal. This would be the ultimate goal. I cannot. I need to replace it by the other guy, by this quantity above, which is the empirical risk. Okay, it's called the empirical risk. Okay, and so of course, I just said the expected risk cannot be computed because the joint distribution is unknown. This is where we started. Instead, we have training data, and so we need to replace these by the thing above. And the logistic regression, SVM, and many other approaches essentially solve regularized empirical risk minimization with convex surrogates for the error loss, which is not computable. Okay, and now we would jump to optimization for supervised learning, but we have no time, so this is going to be left for another day. Should I announce the Monday thing that I'm replacing Big Share? It's already on the web page. As you probably have seen on the web page, so we typically have Big Raj teaching the deep learning lecture, which would be on Monday, but he cannot come due to unfortunate reasons in family. So I will be teaching the deep learning, so you have to put up with me. So if you didn't like this, you can skip Monday morning. I'm going to give the deep learning introduction to deep learning, and I will put the optimization part there. Actually, it fits better in there than in here. Okay, we will do this optimization part. Just before I go, let me just show you the last slide. This is not. I will not talk about these as much. I just wanted to show the last slide. Whoops. No, this is better like this. It gets all the animations that way, so. Which is recommended reading, okay? What's wrong? Oh, come on. Why isn't it showing the last slide? Okay. So this is recommended reading. If you're looking for books to learn about, good books about machine learning. So the one on the left is my current favorite, Ben Recht. I mentioned him twice today, and Maurice Hart, Patterns, Predictions, and Actions. It also has a couple of chapters on causality, and it has chapters on reinforcement learning and all the stuff. It's a very, very good book because it's in every topic, it focuses on the essence, on the essence of the ideas. It's not technically very deep. It's kind of reasonably easy to read, but it's an excellent book. I really love the book. Then there's a much harder book, Learning Theory from First Principles, from Francis Bach. It just came out on MIT Press, but all of these are available legally online. You don't have from the corresponding authors. So Learning Theory from First Principles. Of course, there's a huge probabilistic machine learning by Kevin Murphy, which is about, I don't know, 900 pages or 1,000 pages. It's huge. And I added from last year, I added this one, which is again an excellent book. It's by Andreas Krause and Jonas Hubota from ETH Zurich, and it's called Probabilistic AI. It just came out like a few months ago, and it has all these basic parts of machine learning. Although it calls it AI, I guess it will sell better. But it's very, very good. It's an excellent book too. Okay, thank you. And of course, I'd be glad to take questions. Yeah, the slide will be available. Sure.
Wait for the mic, please. Please, mic.
It is about the uncertainty. I think it was around page 60 or something like that. There were two types of uncertainty.
Yeah. Yeah. I know exactly, but this is tiny.
Yeah. By the definition, you said for one of them, it comes from the model. One of them comes from the model
Yeah,
and
from the uncertainty in estimating the model.
from the
Uncertainty in
estimating the model.
So one of them, they are both, everything comes from noise in the data, okay? But there's, the noise reflects itself in the prediction in two different ways. So the noise in the data affects the estimate of the parameters, W. So there's uncertainty in estimating W. And there's another way, which is because you know that the data is contaminated with noise, you expect that a new value sampled from this model will have its own variance, its some oscillations. And so this one is aleatoric because you know that you cannot observe noiseless data, it doesn't exist. So there's uncertainty in, if you're expecting to obtain a new point, you know that it will have some noise inherent to the fact that it's being observed. But if you're predicting the value, the noise in the training data also reflects in uncertainty in the parameter that you estimated. And this uncertainty in the parameter will reflect itself also in the uncertainty in the predicted value. And so, and these two components will add. So there's uncertainty in the fact.
For example, you, according to this Bayesian plot, the uncertainty is higher on the edges, on
Here,
the right
like
and
this,
left edges.
Yeah. The fact that the uncertainty is higher on the edges
Yes.
is because the uncertainty about the parameters of the model, which is reflected in the bottom line.
And which uncertainty corresponds to that?
What
one?
changes the variation is the epistemic uncertainty.
Epistemic.
Because the uncertainty about the parameters is reflected in the shape of the functions, not in the uncertainty about around each of these lines. So each of these lines, of course, will have around it another little bar of uncertainty caused by the noise. But I'm not showing that one, okay? So these plot here will has essentially two components inside. It has one component that's constant, that's a constant bar fixed here, which is just sigma 2 or sigma or 2 sigma or whatever, proportional to sigma. And then there's the other thing is a variation that depends on the uncertainty on the model. And the uncertainty on the model reflects as a bigger uncertainty about what the predicted value is, as you are far away from the points that you fitted to the model. In this place, of course, you have a high uncertainty because you are very far away from the points that you observe to estimate the function. If you're close to the points, then you have a lot of a much lower uncertainty because all the functions need to go not very far from the point. Okay, so I don't know if I answered your question, but
yes,
I tried.
I want to understand the difference between these two uncertainties more clearly, but it's helpful. Thank you.
Okay. We can explain it offline again.
Okay.
I'll try to explain it better. Thank you.